has a atomic number of 55. Okay, so the type of radiation that is emitted, we'll come back to that here. And what type of radiation, or sorry, why was this type of radiation especially dangerous for the medical providers and emergency responders? Did anybody have a thought on that?
Um, what I had discovered is that um, so cesium-137 itself
Mm-hmm.
produces or emits beta
Mm-hmm.
particles,
Right.
but its daughter product,
Mm-hmm.
barium-137,
Mm-hmm. Mm-hmm.
is even more so penetrative
Right. Right.
than the original material.
Mm-hmm. Mm-hmm. Right. Right. So I was just looking for the first level of decay. If you can find that in your formula, so it'd be the 137. Let's write it out. What's the type of radiation? What did I ask for that on question 2? What type of radiation? Yeah. So let's write that formula here real quick. Clear my thing that's in the way here, and see if we're all on the same page for this here. It is the 137 and 55 here. Cesium. And when it decays, it's going to form 137. So this is, if you have this answer in, that's fine. 56 and daughter barium. All right, and again, there's it can continue to decay, but and that's part of the reason that it's so dangerous, right? Did anybody find the half life for that? Or you can even just look it up now if you want.
30 years. Oh, 30
30,
years?
30 years, yeah. So obviously that could last quite a long time if you have a really large amount of it, which they kind of did. Okay, so you have that. That
30
goes
years or
well with.
300 years? I don't.
Oh, let me pull that back up too, so I don't have that memorized either. Mm, Cesium 137 half life. Yeah, 30.08 years. So yeah, so certainly going to last a long time, and I'm just trying to indicate this is an additional um, loss of energy there too. So it means it can continue to decay. So the barium is not a stable element yet. But this is all I'm looking for. If you have that, that's fine. Because again, we didn't go into much more depth on this, so that was plenty. Okay, and then why was this type of radiation specifically dangerous for medical providers? What's your thoughts on?
Um,
Well, they'd have to be in close proximity to,
Mm-hmm.
the infected, and
Right.
that's yeah. Prolonged exposure will.
Right. And because you have
Oh,
both the beta and the gamma, these are the two types of emissions that we talked about being the most dangerous, right? That it's the hardest to protect yourself against. And it's
yeah.
pretty hard to be treating somebody who's emitting gamma radiation, behind a concrete wall if you're actually working with them, right? Like the providers that did have to go in and work with them. So they had to wear protective gear, but it would be very hard to protect yourself from both types of radiation, right? Definitely. Okay, I'm just going to try to close that so we can slide on down here. Did you guys have this information? Because I'm going to have to clear it to slide down, otherwise it's going to look super messy for us. Okay. All right, and then how far can this type of radiation travel? So if you're talking about just the beta, how far can the beta usually go?
About 10, about 3 meters
three
or
So
10
meters.
that's
foot.
not too far, right?
Yeah,
But
Yeah.
gamma, how far can that go?
about 30 meters, 10
Right,
times that.
quite a bit farther, which is what made this so dangerous, right? Okay, and then what materials or protective measures were needed to block and reduce the exposure to the radiation? For those of you who watched it.
concrete.
Mhm.
Well,
Right. Because it was
Um,
originally in that lead cylinder, right? Which was
right.
keeping it contained. It wasn't necessarily bothering anybody until those, you know, scavengers, the metal scavengers found it and thought, oh, hey, this will be worth something, right? Yeah. And then they had to put the concrete around it. Yeah. Okay. And then, so what were the symptoms then that some of the people exhibited that were
nausea,
exposed?
diarrhea, headache,
Right. Mm-hmm.
Dizziness, organ
Mm-hmm.
failure.
Right.
hair
Right.
loss.
Right. And it got very serious toward the end for those who passed away, right? Yeah.
Yeah.
Hair loss was one of them. Yeah.
It was pretty sad that little girl didn't make it.
Yes, I know it's really, I think that's for me, that was the big impact of the story was like,
And how she ingested it. Well,
right, right.
yeah.
Because
She didn't
when
wash her
people
hands.
don't know what they're dealing with, and I mean, they did it so innocently, like, it's so tragic given that the father thought he was bringing her something really special to play with, right? And then
Mhm.
worked out so tragically. Yeah. Anyway, explain how those radiation affects the cells and tissues. So for beta radiation, how does that affect us?
It affects our DNA. It, if I remember correctly, um, the oh, I can't remember the terms used, but
That's okay.
um, the cells
Mm-hmm.
multiply rapidly, I think.
Mm-hmm. Mm-hmm. Yeah, cells that do multiply more rapidly, and this is more of a physiology thing than chemistry, so I'm not expecting you guys to, know all the ins and outs of that. But when cells are more rapidly dividing, they're more easily affected by these kinds of things because their DNA is being replicated. So if you affect it, it will change. It'll change, and then all its daughter cells will also be affected, right? So that's how tumors and some of those things can start because cells that are already rapidly dividing are more easily affected, and then they have a more dramatic, like if they change, that they'll keep producing the mistake, right? So they have a greater impact than if you hit more mature cells that are not dividing rapidly. It may affect them, but they're not going to have as many daughter cells with the same problem, so it's not going to be as big an issue. So children that are growing quickly, or tissues like your bones or skin sometimes is more rapidly dividing. So those tissues are more affected by the radiation. And gamma radiation really is very detrimental to our DNA. The beta radiation, when it gets in, it also damages the proteins and molecular structures in our DNA and our proteins in our cells. Right? It doesn't go as far, right? But when it does get in, it really causes a lot of damage as well because of all the energy it's releasing. Okay. So that's a long explanation, but basically, if you put in something there about how it affects your DNA, messes up cell replication, that kind of thing, anything like that, it's fine. So once you've messed with the DNA, obviously that creates abnormal cells, and can cause all kinds of various problems for sure. And then which groups of people were most at risk? We kind of mentioned this already, but what was your thoughts on it?
Children and pregnant women, fetuses.
Yeah, yeah. The people that had it closest to them for the longest time, for sure, right?
Mm-hmm.
Yeah, definitely.
That was pretty heartbreaking to see.
Mm-hmm. The thought that hit me, and this is more from a public health perspective, is that when you have communities where people aren't necessarily educated on this, like none of those people had taken a chemistry class in their lives, probably, right? So when they found this stuff, they had no idea they were getting something dangerous, right? So educating and public education around these things, and of course, never leaving something like that where people who don't know what they're getting into could possibly get to it, right? Obviously, it was the government and all the regulatory bodies that were supposed to have taken care of that had really dropped the ball, and that's why the incident happened. But I think people are at risk when they don't have that knowledge, right? They don't know to
Mm-hmm.
protect themselves, and so I felt like that was one of the things that the story really brought out. And it kind of puts more responsibility on people who do know, right? And to make sure that those things
Yeah.
don't happen. Yeah, the number 9. How was this radioactive contamination problem eventually sort of resolved?
They
So
isolated, properly disposed of the waste.
Mm-hmm. Right.
had to isolate the waste, put them in special drum
Concrete.
tubs.
Yeah.
Mm-hmm.
Um, they had to demolish houses,
Yeah.
Yeah. Yeah, to
transport
decontaminate.
to an isolated location
Mm-hmm.
away
The soil
from
was,
the city.
Mm-hmm.
yeah,
Mm-hmm.
the soil was scraped and covered with concrete.
Right. Right.
Yeah.
Yeah, that was
Mm-hmm.
pretty interesting to see that
Yeah.
that part.
And it was so tragic too, right? Because people's homes,
Yeah,
their lives, everything got so disrupted because of that, right?
even their
Yeah.
well water that was tested.
Right. And the water
Yeah.
system got contaminated because it hadn't been contained quick enough. Yeah. Yeah. It was a
Hmm.
very serious situation. And of course, it took a lot of effort to solve it and a lot of public education because nobody wanted that material brought into their area, right? Even though
Yeah.
they had found that more remote location that was really ideal to store it, it took a lot of work to tell the people in those areas that this wasn't going to be a problem for them too, right? So, it's a big job when you have learned and the information. It's a real challenge sometimes, not just in this particular situation, but to try to communicate that information to people who don't have the same training and understanding, right? So particularly as medical providers, it can be very tricky. Like if any of you decide you're going to be working in oncology, right, being able to explain to people what their medication is going to do to them, how it's going to affect the people around them, and all of that can be kind of tricky. Okay, so go ahead. Was there a question? Yes, no? Okay. Do you think the situation was handled wisely by the medical professionals and the government officials once they found out about it?
I think eventually they did, but to begin with, they were
It
trying to
was,
place blame to any other agencies but
Mm-hmm.
themselves.
and
Yes.
So
for communication.
yeah,
Yes.
so they didn't have anything in place. So the clinic that so the folks that abandoned the clinic
Mm-hmm.
didn't really have a solid, I guess there's no policy
Mm-hmm.
or
Mm-hmm.
regulation about reporting and
Mm-hmm.
those
Yeah,
kinds of
they had dropped the
things.
ball badly, badly, yeah.
But
And
eventually
mhm,
they worked together and
right.
it got
Mm-hmm.
handled.
Mm-hmm.
Apparently, it's now whatever they did is now the gold standard
Mm-hmm.
for
Mm-hmm.
um decontamination.
Right, right. So, I think that the thing that really stood out to me was if that one doctoral student who knew about it, right? He had the chemical and the academic knowledge. If he had not stepped in and tried to help when he did, the problem would have been exponentially worse, right? So it's impressive to me how somebody with knowledge can really use that to help those around them, right? He wasn't responsible for any of that. It was not his job,
Oh, he
all
was
of
on
that stuff,
vacation.
right? Yeah. And he got pulled into it, and really, if he hadn't taken it seriously and done what he did, it would have been a completely different outcome, right? Because everybody else took a little bit longer to get there and come to the table, and he was good at convincing the public too about how to handle it and educate people. So I thought that was a key part of the story as well. And then what mistakes were made?
Mistakes, again, not having a solid plan or clear communication to
But
not put people in panic mode.
Mm-hmm. Mm-hmm.
Um,
Yeah.
and then and then also the fact that, they used a lot. I suppose there is a need for that, but the use of police officers and stuff like that, it just created more panic, I think.
True. True. But then they also had the problem of people weren't listening to them, right?
Yeah.
And they didn't, and, as particularly the original community, they didn't want to be accused of stealing something or you know what I mean? They were very
Yes.
leery of getting in trouble when they didn't think they had done anything wrong, and they really hadn't done anything particularly wrong. They just didn't know what they were doing, right? Yeah, it was really an interesting piece because it really speaks to the challenges that public health professionals have to try to educate the public and explain and deal with it in a way that doesn't upset people more than necessary.
I
So,
found it pretty interesting that the hospital was on strike in the movie.
yes, that was very
Yeah,
interesting as well, wasn't it?
yeah.
That providers didn't want to have anything to do with that situation for the most part. Yeah.
Hmm.
Until it came to that man's surgery on his arm.
Mm, yeah. Yeah.
That was
I al-
something.
Yeah, it was really interesting, wasn't it? Yeah. And
Yeah.
I also found it interesting how the international experts from Russia and some of the places where Chernobyl had been dealt with and stuff like that, their experience and their expertise was helpful to an extent, but since this situation was so different, they really had to totally reinvent all the protocols, right? That would normally have been used for radiation exposure in other situations, right? So again, knowledge of what you're dealing with is so important, and being able to adapt to the situation is really important, right? So that was fascinating to me. Okay, so if you'd been a medical professional involved in an emergency like that, how would you have helped educate the public about radiation safety? And obviously, this is a hard thing to put in one simple sentence, but what were your thoughts?
To get tested.
Um, the
And
first
then
thing is
to
clear
get
communication for
yeah.
me. You got to tell
Mm-hmm.
people that people don't know what they
Yeah, that's
are.
true.
Mm-hmm. Oh,
Yeah.
yeah,
Them what it
exactly.
looks like, define,
Mm-hmm.
give it a picture, what it
Mm-hmm.
is,
Mm-hmm.
what the symptoms are,
Mm-hmm.
the risk, like who would
Mm-hmm.
be most at risk, if you're
Mm-hmm.
within this 40-mile radius of this
Mm-hmm.
area, then
Mm-hmm.
you're more at risk than somebody outside that
Mm-hmm.
perimeter, right?
Right,
Those
right.
kinds of things. And also, I think that doing the triage in one large stadium, I think it just creates more chaos than it is anything. And
Possibly,
people
yeah.
who might be from the outer radius come
Mm-hmm.
in there and get contaminated by other people
Mm-hmm.
in
Mm-hmm.
that same
Yeah,
vicinity. So,
that's possible. Yeah, it's too bad they couldn't have maybe taken the testing out to the people first and then sent people over there.
Yeah.
yeah.
They could have maybe done it the
Yeah.
other way around. Yeah,
And
that's
maybe,
true.
like during COVID,
Mm.
you try to restrict some kind of movement,
Mm-hmm. That's
um,
true.
stop
If they had
public
done that sooner.
transportation.
Hmm. Yeah, that's true. If they had actually said, okay, let's freeze public transport until we can figure this out, they didn't because they thought that would scare everybody
Yeah.
too much.
Yeah.
But possibly, and I think now with modern technology, they didn't have an ability to put out a really nice public service announcement on social media and try to. I mean, they could have used radio and TV, of course, but they were so worried about scaring everybody, right? I
And
think that they were
and then
overcautious.
yeah, and then also another thing is, I don't know if this is related to this question, but one of the patients doesn't know how to read.
Mm-hmm.
So,
Mm-hmm. Mm-hmm.
having like we have today, we have pictures that
Mm-hmm.
on
Right.
say
Pampered.
like
Yes.
a fire hazard or something. If you
Mm-hmm.
have
Mm-hmm.
pictures, at the very
Mm-hmm.
least, that people who can't read or whatever, they could kind of
Mm-hmm.
make a guess that this is not a safe thing.
Right, right. That's true. We don't really have like even when you guys go into a chemistry lab and stuff now, there's lots of different symbols on different packaging and stuff, right? And someone in the general public doesn't necessarily know all those symbols, right? So maybe more public service information on some of those would be good. I know there is a lot. Like I think we are all fairly familiar with a radioactive symbol or something like that, but not necessarily everybody is, right? So teaching people that kind of thing would be helpful. Yeah. And
And
explaining to them with pictures like you're describing of what's going to happen
and
on both
probably in
sides.
the 80s they didn't those kinds of symbols and labels are
Mhm.
not
Yeah, I don't
um
think they had it as well
what
established
they
as it is
yeah.
now. Yeah, absolutely. Yeah, yeah. Because it's unfortunate if it had been all over that original lead canister and those people that originally scavenged the metal would have seen
Right.
that, they might have known right away, oh, don't touch that, right? Yeah, could have saved a lot of problems. So, what information would have been most important to communicate to prevent the panic? And I think maybe we've answered this question, but teaching people about the basics in terms of safety from radioactive activity, right? Staying further away, making sure that you don't actually come into physical contact with it, and that sort of thing, containing it, and that's, yeah, isolating it. Any other thoughts? Okay. And then how can healthcare workers prepare for future radiological emergencies? Any thoughts on that? Since hopefully, we don't have to deal with that in our professional lives, but there's always, in real life scenarios, that is a possibility.
um
Establish
Maybe
plans, training.
Yeah,
Training.
training. Maybe the doctors and healthcare providers should be able to identify radioactive symptoms
Mm-hmm.
quickly.
Mm-hmm.
Um, because
Yeah.
in the beginning there, they had individuals from multiple ho hospitals, and they
Mm-hmm.
eventually put them in one spot
Mm-hmm. Mm-hmm.
because
You're
they
right.
didn't
It took them a while to
identify
identify
what the
it.
problem was.
Mm-hmm.
Yeah.
Right. And if that one doctor, if I remember how it kind of went down, if that one doctor hadn't made the right call and talked to his friend,
Yeah.
and figured it out, they might have gone on thinking they were dealing with a really bad flu, right?
Right, because the symptoms are not generally the same, but not really.
Mm-hmm. Right. They were diverse enough, and fortunately, they picked up on the fact that the nausea, the skin burns, and the rashes and all of that was fitting a really clear picture, but they may have missed that, and if it had gone on any longer, there would have been that many more people that would have been exposed. Yeah. And then these last two questions are just in terms of nuclear chemistry, what are the most interesting parts of the series for you? Those of you who watched it, what did you find interesting?
How
How the
harmless they
dust,
look,
yeah, and how
Mm-hmm.
the dust
how
glow.
pretty they are,
Yeah,
Right.
and
So
and
cool.
it's I don't know, it just appears that there's in terms of quantity, I didn't see a whole lot of them, but
No,
the
they're very little.
damage
Mm-hmm.
and
It
how
doesn't take a
rapidly people got sick.
Mm-hmm. Yeah. Yeah. Yeah, I think for myself growing up, I've always thought of radioactivity in terms of like Chernobyl, right? A big explosion, something really dramatic. And this was very subtle. And that's why I found this so interesting, is that it was definitely, people
Yeah,
didn't get
it's
scared because it
powder
wasn't blowing
as
up, it wasn't
yeah.
scaring them, right? Mm-hmm.
Yeah, to me, in my head, when you talk about radioactive, it's like um, light rays or
Mm-hmm.
something like
Right.
that. I didn't imagine it could be in the form of powder.
Mm-hmm. Exactly. Yeah, you don't necessarily think of it that way. Yeah. And again, most of our exposure in our education on this has been, history about Hiroshima and Nagasaki and, Chernobyl, stuff like that, where there've been very much dramatic scenarios. And we know that there's lots of fallout for a long time afterwards, maybe, but we're not as familiar with this kind of contamination. So, all right. Well, thank you guys. Hopefully,
the
if you haven't
one
go ahead.
the one thing that caught my attention is how that guy survived his surgery,
Mm-hmm.
and they had to rotate between the
Yeah.
nurses, the doctors, and whatnot, just to finish his surgery.
Yeah. Yeah.
That was pretty interesting.
It was interesting, and then the fact that, I mean, the doctors that went back in, even though it was a risk to them, and the,
Right.
the people that did, I mean, as a medical provider, sometimes, and I think they made that very clear in this movie, sometimes you have to decide between your call of duty and your self-preservation, even, and fortunately, none of them, had really, really bad outcomes, but it was a real risk, right? And I think
Yeah.
now in contemporary terms, we have Ebola outbreaks, we have stuff happening, and it can be a very real thing, right? As a medical provider, you are at higher risk for certain things, and it's something to be aware of and kind of reckon with. So, thank you for bringing that out. All right.
Mm-hmm.
And then that last question is just, what did this series teach you about the role of nuclear chemistry in medicine and public health? Any other?
Well, it's good if you use it properly and correctly,
Right.
and it's bad if it's mishandled.
Absolutely. Right. Yeah. And I think that's one of the things where sometimes we get so wrapped up, like those companies that left the stuff there, and the legal issues around something, that we forget to really, follow up on the basics of, we just have to protect the public, right? And they kind of let those other legal issues predominate in their decision making originally, right? Instead of forcing their way in and making sure that was a cleaned up site, they just, like you said earlier, they blamed other people, and they let it happen, right? And that was really unfortunate. So anyway, for those of you who didn't watch the movie, hopefully we've made you curious. Again, nobody has to do this particular project. If you'd rather do the test on chapter 5, that's fine. But if you'd like to do this, I think it's a great way to kind of think it all through and get a good exposure in terms of understanding the implications in the real world. Okay, so let's jump in with our first section in chapter 6. Oh, you know what? Before we do that, did everybody get my emails about the labs and the lab
Yes.
kits and stuff? Okay.
Yeah.
Okay,
Yeah.
good. Any additional? I know some of you have gotten them and many of you have not gotten them.
No.
I did not get mine yet.
Yeah, and this is, I mean, that's a fairly significant problem. So I am hoping that, well, the good news is that we've got the lab cleaned up today.
Oh, yay.
So that was a good thing. The problem is that we still have some broken pipes in the building. So I
Yeah.
still have to wait before we can actually be in there doing chemistry classes until that gets solved. And that, I don't know how long it will take. I truly hope it'll be quickly. And if it does take a little while and there's still a lot of labs that people aren't able to do, we will take the last several weeks of the class and do some in-person labs for those of you who can. And hopefully those of you who are out of town will have gotten your kits by then. I know, Esther, that might be a problem for you though, right? Because have you gotten
Yeah.
yours yet?
I haven't gotten mine yet.
And you're not in town either, yeah.
No.
I have talked to them multiple times now, and they keep saying that it's not a problem, but some of you have had yours sent back twice already, I understand, correct? That the airlines are not,
I think so. Yeah.
yeah, they're just not taking them on the airline. So I'm not sure how to track this down any better. She did give me a link today that says you can track your packages.
Would there be any way for me to like fly out for that?
I mean, if
Or would that be
I
under
would
my
have to
own,
talk to the
my
college, I
own
think that
expense,
might be a
or
great idea, if it comes to that. If you're willing,
yeah.
that might be the only solution we can come up with is like, yeah, we're going to do a long weekend of labs and fly you in. But hopefully we can get things sorted out very soon. But this is the first time we've had this trouble with the kits being sent back. So I don't know if airline regulations changed, and I have no idea why they aren't seeming to understand why that happened either. They just keep resending it, and I, they're not
It's
giving me a
always
really good
quite the hassle
explanation
to get
either. So
anything out this way. There's
yeah,
a certain steps you got to take just to
exactly.
get certain. Yeah, there's hazmat. It takes a while.
Hmm.
Anything, it takes a
Right,
while.
right. So I'll keep emailing her, but yeah, I'm not sure what we're going to be able to do there. If they could just remove whatever it is in the kit and send it without it or something, I mean, we could always modify
Oh,
things, but
I
I'm not
learned
sure.
that. I learned just recently that any kind of ammo, you can't have anybody on the flight for any ammo that's shipped in for any hunting that we do out here. So it's pretty interesting. I
Oh,
don't know
wow.
how
Yeah,
they
that's a
do
lot of
that here.
limitations then.
Yeah,
Yeah. And I
yeah.
imagine that
So
you're right. The smaller planes are going to be very different than the major airlines that they're dealing
yeah,
with. And so they probably are not necessarily checking all of that out. So,
yeah.
okay. Well,
It goes the
worst case
same with the
scenario,
batteries and
we will
whatnot. So
try to fly
it's
you
it's
in.
different. It'd be something. It'd be nice.
Yeah. Yeah. I think
Yeah.
that might be an option we have to consider. So, all right. Lexi, I know you've gotten yours. Is there anybody else that's outside of Utqiagvik here that has not gotten their kit? I know Trishta hasn't gotten hers yet, but she's traveling. Anybody else? Okay, so the rest of you are in town here, and we could probably get together and do labs potentially.
Yeah.
Am I getting that right? Okay, excellent. All right, and then I will, as soon as I get some dates from the NOAA Observatory, I'll be able to let you know when those field trips will be available as well. So, okay. Well, we've had a lot of conversation. We better get down to this chapter and get going here. So we'll do this first section and we'll take a break. All right, so we're going to be talking about the molecular compounds. This time we talked about ionic compounds a lot previously. This time we're going to be going over more of the molecular compounds, so our covalent type bonds. Okay. So our learning goal is going to be able to look at those formulas, give the correct names, given the molecular compound, be able to write the formulas out. Okay, so you've probably seen some of these structures before. This is the Lewis structures again for those molecules where you have the electrons represented as dots, and then the lines are showing shared electron pairs, and we call those the bonds between the two molecules. So you use the symbols, O for oxygen, C for carbon, and then we show their bonds here with the line which just means they're sharing 2 electrons. So the line really equals 2 electrons that are shared between those 2 molecules. And in this case, they have a double bond, so they're sharing 2 sets of electrons on this side and 2 sets of electrons on that side. And the same with this. This is with carbon monoxide. You have 3 sets or 3 pairs, so these would equal 6 electrons here being shared between the carbon and the oxygen. Okay, and then the ones that are not being shared, we illustrate them as being on the other side of the symbol in a pair like that. Okay. Esther, do you want to read us this slide?
Covalent bonds. Core chemistry. Do you mean to read that part? The core chemistry still?
You don't have to read that, no. You can just read
Okay.
the
I said that.
no problem. That's
Molecular
okay. Either way.
compounds, yeah, form when atoms of 2 or more nonmetals share electrons and form a covalent bond. Valence electrons are shared by nonmetal atoms to achieve stability. A molecule is a discrete group of atoms in a definite proportion.
So again, molecules are those different atoms or different elements on the periodic table. Sometimes it's 2 of the same too, but oftentimes it's multiple different types. And they've decided to get together and share their electrons, or in the case of ionic bonds, give one electron to the other, and then they're really bonded tightly because of the kind of the charges that attract them to each other, like little miniature magnets. Okay, but this time we're talking, like I said, mostly about covalent bonds. Alan, can you read us this slide?
Oh, yeah. When naming a molecular compound, the first non-metal in the formula is named by its element name, and second name is named using first syllable of the name followed by IDI.
Yeah, we pronounce it "ide."
When a idea when a subscript indicates 2 or more atoms, an element, a prefix is shown in front of its name.
Perfect. So here you can see on the table over
So
here.
prefix use name molecular compounds: 1 mono, 2 D, 3 3, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, 10 deca.
Yeah, so di, tri, mono, and some of those are pretty familiar to us, and you'll be seeing that a lot as a prefix in front of the name of the nonmetals in covalent bonds. Sometimes it's the first one too. So just to make it clear, the first one, if there's just one of it, is just going to be its element name, right? If there's 2 of them, then you're going to add the prefix to the first one as well. So it might be like dichloride, something, right? And then the second one, again, if it's just one, then it may have mono in front of it, but it may not. Some of them do have mono, some of them don't. But it will have the name changed so that it will have "ide" at the end if it's the second non-metal in the compound. And it's usually not too, as you get into it, it's like you're probably wondering, like, how do I know which one's the first one and the second one? But the way they're written out, you'll be given one form of the name so that you'll be able to deduce which one is the first or the second, right? You're either given the formula or you're given the name. You don't have to try to figure that out. Okay. Aiden, you're next on my list here. Can you read us this one?
Names and formulas of molecular compounds. Several compounds may be formed by the same 2 nonmetals. The number of oxygen atoms present is indicated by the prefix. When the vowels O and O or A and O appear together, the first vowel is omitted.
For example, monoxide, right? It would be mono and then oxide, but it would be like monoxide if we put both those in, right? But we just say monoxide, right? So we take out that second O. Or if there's an A and an O, we just take the second vowel out. Makes it a lot easier to say the word. So you can see in both cases you have 2 nonmetals, carbon and oxygen, that make these compounds. and with different chemical formulas, they have to have different names so that we can tell them apart, because these are very different things. Carbon monoxide and carbon dioxide have completely different physiological effects on us and our environments, so we don't want to get them mixed up, right? So we have to have ways to differentiate between the two of them, and those are these happy little prefixes. Any questions there? Okay. And whenever you see no in chemistry, it's actually nitrogen monoxide. Okay? All right. Okay, so just a quick trial here. We're going to experiment a little bit more later, but if you see these formulas, what would the names be here?
Carbon dioxide.
Carbon dioxide, uh-huh. This is also carbon, and then this is sulfur, so what would this be?
Disulfide.
Carbon disulfide. And then we just saw this one.
Nitrogen oxide.
Nitrogen oxide, very good. And then if we have two nitrogens, what would it be then?
Dinitrogen oxide.
Very good, yes.
Oh, cool.
And then if you have 6 fluorides in this one, so you have sulfur, hexafluoride, very good, yeah. And then here, what do we have?
Sulfur dioxide.
And then again, same elements, but different
Sulfur
formulas. So
trioxide.
now we have, yes, sulfur trioxide, very good. Excellent. And you can see those uses as well. And because they're so different, you know, in terms of some of them are toxic, some of them are totally inert, you definitely need to be able to tell the differences. Here's our answers. You got those all right. Okay, so this is going to help us work through kind of the same process we just did, but it'll break it down for us so we make sure we got it. Here you have a compound, or a molecular compound, Cl3, right? And we know that is nitrogen and chloride. And then we need to be able to come up with the name. So the first step is to decide what the first nonmetal is, and we know that is nitrogen. And if I could just get my annotate to close, we can go to the next one. Okay, and then step 2 would be to figure out what the second nonmetal is and add the "ide" to the end of its name. So we take chlorine and make it chloride. Then step 3 is to add the prefixes. So there's only one of the nitrogen, but how many do we have of the chloride?
3.
Right, and so what prefix do we need?
Tri.
Tri.
Right, very good. Excellent. So once we put that all together, we have nitrogen trichloride. Okay, so here's another example. We have B2O3. What is that going to be?
Diboron trioxide.
That would be reasonable. Let's see if I can actually spell it quickly. Boron.
Yeah, I was right.
Try. my finger is not
Kinda
working like
guess.
that today. Oxide, right? Okay. And you guys all, I think, you know, you've heard these terms enough. It's pretty easy for everybody to add that "ide" on there, right? It just sounds right. So that's good. All right, so it's going to walk us through everything here, but the B was boron, so we identified that. And then the second one was oxygen, and we changed the oxygen to oxide. Then we added our prefix tri and di, and we ended up with diboron trioxide. Any questions so far?
No.
Okay. And it's funny to me how, like, it seems so concrete and obvious, and then when you go to actually do practices, there's just so many little steps that it's really easy to mess these up. So I know it seems like it's laborious sometimes to go through all these steps, but it's really easy to miss stuff when they have all these little petty details, so bear with me. I'm going to make sure we cover all those steps each time. Okay, so Alexi, can you read us this slide?
Yes. In the name of a molecular compound, the names of 2 nonmetals are given along with prefixes for the number of atoms of each. To write the formula from the name, use the symbol for each element and a subscript if a prefix indicates 2 or more atoms.
All right, so now we're just reversing the process, right? Now we're writing the formulas. So what would this formula look like? Esther, do you want to try to write that formula out for us? And if anybody wants to help her out with that in terms of just talking about which elements we're dealing with. Our first element is what?
Phosphorus.
Phosphorus.
And
P.
that's a P. Very good. Is your annotate working okay, Esther?
It's not letting me for
Oh,
some
okay.
reason.
Sorry. Okay.
Yeah.
Yeah. Trishta, do you want to give it a shot? Is your annotate working? No. Go ahead, Aiden. Very good. So P2.
Me too.
And what's our next symbol? Oxygen. Very
Oh,
good.
oh,
Um,
O5. Very good.
I-
Perfect.
yes.
Nice co teaming up there. And I just made up a new word there. Okay. Yes. So we have P2O5. Very good. So in order to do that, of course, we figured out that phosphorus was our first element and oxygen was our second. We figured out what prefixes we were going to need. Di for phosphorus, because there was 2 of them, and penta for oxygen, because there was 5 of them. Okay. Is there a second one? Nope. Okay. Excellent. Okay, so our next question here. Shanae, can you read us this slide?
Compounds, ionic or covalent. A compound is usually ionic if the first element in the formula or the name is a metal or the polyatomic ion NH4. K2O, K is the metal, the compound is ionic, potassium oxide. Covalent if the first element in the formula is a non-metal. N2O and is a non-metal. The compound is a covalent dinitrogen oxide.
Perfect. So keep an eye out for this tricky little ammonia, right? Because as an ion, it's a positive charge. So it acts as if it's a metal. So just take a good long look at it and make sure you remember that, because it will show up many times and it will look like it's a non-metal, right? And so it can be very confusing. But in fact, it is a positively charged ion and behaves as if it was a metal and makes ionic bonds. Okay. So don't let it fool you later. All right, so this is the chart that we've kind of already covered. We talked about the ionic compounds all last time, and we've gone over some of the details here on the first nonmetal, second nonmetal, how we do those names. So any questions on anything on the chart here? It is a nice reference. If you are like, some of us really like flowcharts. I don't always think in terms of flowcharts very well, but they are nice as a reference for quick decision making. And you should all have this in the slides I sent you, but if you want a screenshot, go ahead. Okay. All right, so quick learning check here. Let's see. Shanae, if you want to give us a hand here with your annotate, you can circle the answers for us as we answer them together. Select the correct name for each compound. So this first one is what? What is that?
Silicon tetrachloride.
I believe you are right. Very good. All right. And the second one, what is that? A P2O5. What would we call it?
Diphosphorus pentoxide.
Very good. And our third one, Cl2O7.
Dichlorine heptoxide.
I know, what a fun word, right? Heptoxide. Good. Excellent. And you guys are right on track. Very good. All right. Next here, we're going to identify each compound as an ionic or a covalent bond and give its correct name. So first of all, we'll just yell out whether it's ionic or covalent, and then somebody can just yell out the names. What is A? Ionic?
Covalent.
It looks like it would be covalent, right? Why is that?
Sulfur.
Is
Our first one. Our first element.
right, and it's a
Non-metal.
yes, exactly. I know you're already thinking all those things, right? But just so we're all clear, right? This is a non-metal, so and it's not ammonia, so this is a covalent. Let's just put a C there for covalent. Okay. And our next one, what is it?
Ionic.
Looks pretty ionic to me, yes, because why?
The first element is a metal.
Very good. Right. It is barium, right? Very good. So we have what is the name then?
Barium dichloride.
Now remember, if it's ionic, we don't have to worry about those.
Oh,
So this could just be barium chloride. But that was a fair thing to say. If it is covalent, then you absolutely have to use the prefixes if there's more than one, right? And sometimes even if there's one, you still put the mono in because we have to differentiate naming wise, like with carbon dioxide or carbon monoxide. It's helpful to have those extra prefixes in when there's just one, just to make it more clear because they're so different. So again, when you have covalent, you must use the prefixes, but if it's ionic, it's kind of understood. So you can just call this barium chloride. All right, here's our tricky one here for C. What is this? Ionic or covalent?
ionic.
It is ionic
Ionic.
because why?
That
Helium is the element.
It's ammonia, right?
Mhm.
Yeah, this guy here is ammonia. We don't call it nitrogen tetrahydrate or something like that, right? We call it ammonia. So, and it is what? Positively charged, right? So it's going to form ionic bonds with this phosphide. All right. What's our next one? Ionic or covalent?
Ionic,
And why is it ionic?
because there's copper.
Mhm.
Do you call it dicopper?
Nope, because it's ionic, right? So we can just
Okay.
call this
Copper.
copper
What's it?
carbon.
Cobalt?
Cobalt.
Not cobalt. Nope, this is a polyatomic
Carboxyl.
ion.
Carboxide.
Nope. Is it
No.
carbonate or carbonite? It's a polyatomic
Oh.
ion, right? It's one of those tricky guys that we were trying to memorize in our table, right?
Yeah.
Right. So when you see them together like this, and we know this is an ionic compound because this is a polyatomic ion and this is a metal, it's an ionic bond between these, the CO, instead of it being carbon trioxide, we call it,
Carbonate.
exactly. Thank you. All right. So that's why there's just so many little tricky nuances to, kind of mess us up on some of these things that we have to be wary of. All right. Our last one here. What is it? Covalent or ionic?
Covalent.
Covalent.
Covalent. And it's covalent because
The
That is-
non-metal.
the non-metal. Very good. And so how would we name it then?
Di.
Dinitrogen
Nitro.
Tetraoxide.
Very
tetroxide.
good. Very good.
Tetroxide.
Yes.
Tetroxide.
It's a mouthful, a definite mouthful. So here we go. The first one's covalent and it's sulfur trioxide. Very good. The second one was ionic because it's barium chloride. And the second one is also ionic, ammonium phosphate. And then D is ionic as well, copper 1 carbonate. And sorry, I should have mentioned that too. Copper, because it's one of those bipolar sorts of guys, it does have the Roman numerals.
Gosh.
So again, lots of little things you got to think about when you're looking at these. And then our last one is covalent, and it is dinitrogen tetroxide. Get that out right. Okay, so you can see how there's enough little nuances that you just have to kind of pay attention carefully as you're going through these because it's easy to miss some little details sometimes. And unfortunately, if you're actually, doing chemical reactions and things, you don't want to get those things wrong. Make sure you're dealing with the right stuff. All right, so that's the end of this one. Let's take a little break here. Do you guys need 10 minutes or is 5 minutes enough? How are you guys feeling?
Either or is fine.
Okay, it sounds like everybody might need 10. So okay, go ahead and go ahead and move around a little bit, get a snack, get some coffee, whatever it takes. And I'll see you back at 7:35.
Not to brag or anything, but I just inhaled a Big Mac and 10 nuggets in under 4 minutes.
Oh dear. That is impressive, definitely. You were starving hungry for sure.
Oh, I'm sure his parents taught him manners, though.
I wouldn't say that. Don't lie.
I'm sure they did. I do believe you.
Sounds like my 9-year-old son.
Oh, it's amazing how fast you can eat when you're in that right age window. Now, when I do that, I'm paying for it for hours afterwards. For some reason, my digestive tract doesn't like it.
That's how my teenage boys are. 17 and 19-year-old boys. That's exactly how they are too.
Just checking in with everybody. Okay. All right. Good stuff. I think we're right about there at 7:35 almost. Is most of us back? No rush, but
Yes.
okay. Now I know some of you looks like they're texting me, letting me know your internet's not always working great, but if it's working at all, wonderful. Otherwise, I will send the recording out and the slides and stuff. So hopefully that'll be something you'll be able to catch up. And if there's gaps in there, you'll be able to catch up with them later, or certainly let me know if there's something that didn't come through clear and you want to review it with me. That's fine. I do understand internet simply is not one of those reliable things in our lives. Okay.
You would think Sterling could cause, help with the issue, but it goes out every now and then too with Starlink. So, yeah.
Starlink seems to work better for me than my previous types of internet, but yes, it's not infallible for sure.
Yeah.
So, all right. Well, we will jump into our next section here. Again, we're looking at ionic and molecular compounds. And this time we're going to be working on drawing the Lewis structures for the molecular compounds and for the polyatomic ions. So this is going to be kind of more artsy and craftsy, if you will. Those of you who did get your chemistry kits, did you get the little plastic like modeling kits with the little balls and little white bonds that you can use to make molecules, the three-dimensional molecules? Yeah, okay, good.
Yeah.
Excellent. All right, because those of you who didn't get them, I'm going to try to, because we have a whole bunch of them in the lab, I'm going to try to distribute some of them as needed, at least for on loan, so that for this next course or this next section, I would like to give you some fun sort of hands-on ways to assess the learning on this one. So once we're finished the lecture on all this, I will let you know, because I think this one, in my experience, has been one of the hardest things to assess on Pearson, because it's very hard. They want you to try to do the Lewis structures and stuff on the digital platform, makes it really hard to get it right. So I would rather assess this a different way. So if somebody really wants to do the Pearson, that's fine. Let me know. Otherwise, I will provide you with some more hands-on stuff with either the lab kits where you can make the three-dimensional molecules, or the if you can't get one of those, we'll figure out some alternative for you. But I would rather have you guys do it that way. It's a little bit more fun to actually experience the 3 dimensions, and it kind of drives the point home a little bit better. So.
Sorry, I'm back. Sorry, I was just eating dinner.
No problem. Dinner is a good thing to do. Okay, so a molecule is represented by a Lewis structure in which the valence electrons, and again, what are the valence electrons? What are we talking about when we say valence electrons?
The outermost.
The outermost electrons, the ones in those final S and P orbits, right? So, and those are the ones that are free to interact with other atoms and therefore give it the electrical properties, right? So, every atom out there wants to have 8 except for hydrogen and helium, which are happy when they just have 2. Okay, so the Lewis dot structures, as you can see, kind of this is the examples. We talked a little bit about the dots that we used before. This is showing where there's bonds between them using the lines, and we mentioned that last time as well. Okay, so this molecule here, methane, if you decide to put yourself through organic chemistry as well, that's actually where I think the fun starts with chemistry, but you may or may not agree with me when we're done here. Methane is something you're going to see a lot of. Methane is a major core component of organic molecules, this basic carbon-hydrogen arrangement, and so you'll see lots and lots of that in organic chem. And this is what that looks like. Each of the helium has sorry, I said helium. I meant hydrogen. Each of the hydrogens has 1 electron to contribute, right? And then the carbon has 4. So these little, I'm going to mark them red for the helium ones. They're contributing these electrons. And then carbon is contributing the little green ones here. We'll make them green because carbon has 4 outer valence electrons as well. So they share those pairs so that they all have a nice complete outer valence, because the hydrogen just need 2, right? And the carbon wants 8, so they're very happy in this arrangement, and they make those methane molecules. Now here is the balanced, not ionic, but the balanced version here of the ammonia. So how does it set up? Each of the hydrogens has an electron to contribute and share, and the nitrogen has how many on its valence electrons? Remember, you need to find the group and then figure out how many it's got on its outer valence that way.
5.
5, right? So 5 of them are for nitrogen. So let's grab a little blue marker here. So 5 of them are from the nitrogen. So these 2, and then 1 each from these shared pairs is from the nitrogen. And then each of the hydrogens, again, is contributing 1 electron. There we go. So they have, all of them have a full valence, right? The hydrogens just need 2, and the nitrogen has 8 around it as well. And then here you can see for the molecule of what? What is this?
Water.
Water, right? And again, the oxygen has how many to contribute? How many outer valence electrons does oxygen have?
6.
6, right? So it's got these 4 here, and then 1 each for the shared electrons. And hydrogen can contribute 1. And there's your 8, or a full valence for the for the oxygen, and the hydrogen each gets their full valence of 2. Okay, so that's the dot structures that we can, and that's kind of what we're talking about, even though we move to this other structure, because this shorthand is a little bit easier to just draw the bars here, which indicates 2 electrons that are being shared by the 2 atoms on either side of that little bar. Okay, and then when you have some of these, this is the free pair of electrons that doesn't have, it's not being shared. So nitrogen is still sort of hogging these 2. Oxygen's hogging these 2 pairs of electrons, right? It's not sharing those. Okay, so those are the extra free electrons there. not being bonded. All right, so any questions on that so far? We're going to go through it in a little more detail, but I wanted to explain that diagram. Okay. Esther, can you read us this slide?
Yes, the simplest molecule. A hydrogen molecule, each forms as the atoms move closer and the positive charge of the nucleus attracts the electron of the other atom. Has a shared pair of electrons, a covalent bond to give a noble gas arrangement of helium in each hydrogen atom forms when the molecule formed is more stable than the two individual hydrogen atoms.
Mm-hmm. Right. So these form these dihydrogen molecules in nature, right? So most of the hydrogen that's in nature is naturally bonding with another hydrogen, so that you have two little atoms together, and they have to stabilize each other with this nice little covalent bond. Okay. Okay, so here's kind of a diagram of how that works. As energy increases, you're going to have atoms splitting apart more readily. And as the distance between the nuclei decreases, they're going to be more likely to come together. Okay, so the closer they get, the more likely they are to bond. And the cooler they are, the more likely they are to bond, because they're less energetic, they're moving around less, if you will. And so cooler hydrogen atoms that are close together are definitely going to form this dihydrogen molecule, if they can. Right? But as you warm them up, warmer and warmer, you can actually separate them. Okay. All right, let's see. Trisha, if your internet's working, you want to read this one for us?
A molecule is represented by a Lewis structure in which the valence electrons of all the atoms are arranged to give, what is that,
Octets?
octets. Sorry, it's on my phone, so it's a little bit
Oh,
small.
yeah, yeah. It's a strange word, yes.
The
Octets, just
shared
normal sets of 8.
electron bonding pairs are shown as two dots or a single line between atoms. The non-binding pairs are lone pairs are placed on the outside of the atoms.
Right, so this is kind of what we were talking about before. Here's the ammonia molecule, and you have the bonded pairs as the lines, and then the lone pair up here. Because again, nitrogen has to have 5 going into the equation, right? So it had 2 here and 1 on each side, and so it's sharing 1 with each of the hydrogens, and each of the hydrogens brought 1, so that's where the bonds come in. Okay. All right. Nicole, if Eva's there, would you like to read one? I feel like I've been leaving you guys out a lot. If you guys both need to rest, that's okay, but I was just wondering if one of you wants to read this one. If you're still there together.
Read it.
Oh, okay. Go ahead, Alan.
A molecule is represented by a Lewis structure in which the valence electron of all atoms are arranged to give octets.
Octets.
To draw octets,
That's okay.
the electron dot formula for a fluorine molecule. Fluorine
Molecule, is just difluoride.
difluoride, and we start with the electron dot symbol for each fluorine atom. Each fluorine atom share 1 electron to form a covalent bond, giving each fluorine an octet. Octet?
Yeah, it's a tough one. It's octets. Yeah.
Octet, sorry.
Yeah, no, it's okay. That's not a word we use every day. Definitely. Okay, so remember how we drew the dot structures for the elements, right? We start off with looking at what group it's in, and we know fluoride's in group 7, right? So we're going to give it 7 electrons, which means it'll have 6 in pairs, right? And then 1 that's just lonely by itself on one side here, right? And that's what we see here. So if we have 2 fluorines, they would like to hook up and share these electrons here so that they can both have 8 in their outer valence, right? So you end up with this structure here. And you still have the 14 electrons, right? You have 14 electrons here with the 2 combined, and you have 14 here. So you always need to count, make sure that you're not losing an electron sometimes when you're drawing these diagrams. And they have one shared pair between them here. So we can write that this way if we want, right? There'd still be 14 electrons represented here, 6 here, and then 2 here. So we'd have 12 plus the 2 in the bond, and we'd have 14. And then we can write that as difluoride like this. Or a fluorine molecule. Any questions on that? So again, first you have to make sure that you know how to draw it by going back to the periodic table and knowing how many valence electrons each of them has, writing the symbol out, and then, one second, let me shut the Sorry, something exciting is happening behind me here. Okay, yeah, so we first have to make sure we have all the electrons accounted for, and then we can put the pairs together and draw them out. So here it's showing us the elements that typically form these diatomic molecules, meaning that the 2 of them like to hang out together if they can, so that they can each have a full valence octet. Okay, so hydrogens, of course, aren't going to have the octet because they just need 2, but when 2 of them get together, they have that, right? Each of them has 1 by itself, but 2 when they get together. Nitrogen has 5 by itself, but if you get 2 of them together, they have 10, so they can have a pair that they can share. Oxygen has how many in its outer valence? We have 5
6.
here. This one's got 6, and fluorine has
7.
7, right? So when they get together, they can share electrons, and that allows them to have a full valence. So some of them need to share more than others, but when they do, they can have 8 around each of them at least part of the time. And so we call those the diatomic molecules. And these here, generally in nature, are going to form diatomic molecules.
With itself, but not with others in their group, correct?
Yeah, when we talk about the diatomic molecules specifically here, it's just with their own type. So 2 hydrogens, 2 nitrogens, 2 oxygens, like that. Not other types of elements. That will be a separate kind of molecule. Okay, does it make sense? So oftentimes when you get a pure sample of something, like if you have a tank with nitrogen in it, a lot of those molecules in there are not going to be individual nitrogens floating around by themselves. They'll be in a diatomic molecular structure like this. Okay. Okay, so this is, I mean, if you want a screenshot of that or something, this is kind of a reference. These are the ones that would normally do that. Others don't always do that, right? The noble gases certainly don't, because they already have an octet. And most of the others don't typically do that either. But these like to do that because they both feel a little safer when there's 2 of them in terms of their octets. Okay. Let's see, who's next here? Who hasn't read in a minute? Josita, can you read us this one?
Yes. Sharing electrons between atoms of different elements. The number of electrons a nonmetal atom shares and the number of covalent bonds it forms are usually equal to the number of electrons it needs to achieve a stable electron configuration. Table 6.13, typical bonding patterns of some nonmetals.
Right. So again, the covalent bonds are sharing electrons, right? So those that like to share for sure are these here. So boron, carbon, silicon, nitrogen, phosphorus, oxygen, sulfide, fluoride, and chloride, bromine, and iodine. Okay. So in group 7, they have 1 electron that wants a friend, right? So they usually form 1 bond. For oxygen, there's they have room for 2 more, so they can usually hold 2 bonds. All right. For nitrogen, they usually can hold 3 bonds because they want 3 more electrons, right? So they will share 3 electrons in order to get those bonds. Phosphorus is the same. For silicon, they typically have 4 bonds, carbon 4 bonds, and then boron 3 bonds. Hydrogen only has 1 electron to share, so it can only have 1 bond. Okay, and when you play with those 3-dimensional little chemical kits that I'm hopefully going to get to for everybody, the molecule kits, they have just that many holes in them, right? So the carbon, let's say it'll be a little black bead and it'll have 4 holes, right? Nitrogen has usually it symbolizes a little blue one and it has 3 holes. Oxygen has 2 holes, right? And so it makes it easy to understand how many bonds they can form. So I'm going to try to make sure everybody has a set of those to play with as we kind of digest this information. Hydrogen and boron do not need to form those octets because they don't need a full 8 to be happy. Hydrogen shares the 1 electron pair, and boron shares 3 electrons for a set of 6 electrons, and then it's generally okay with that. So there are little exceptions, as we can see here, but for the most part, the ones you're going to be dealing with are these here: carbon, nitrogen, oxygen, fluoride, chloride, bromine, iodine. These ones here, okay, in this class, and hydrogen a lot. Okay, so practicing drawing these diagrams. To draw the electron dot formula for methane, which we'll start with, and I do apologize, I wish they used an example that was a little bit more along the naming pattern that we've learned so far, but methane, you're going to be, you would learn a lot about, I mean, its name makes sense, but it's more in terms of organic chemistry than it is for this, because otherwise we should call this carbon tetrahydrate, right? But we don't, we call it methane. And again, that's because it's part of an organic chemistry system that it's a little bit different. But first of all, let's draw the dot structures, right? For carbon, we have how many little electrons around its valence?
4.
4. And then we have 4 of the hydrogens with 1 electron each, right? So then we're going to mix and match them so that we end up with this. And I just can't move the picture so that I can see that, like you guys probably can. Anyway, yeah. Here's our structures when we get them together, right? If we draw the Lewis structure. So these electron pairs are being shared so that we have an octet rule for carbon. And again, because hydrogen only needs 2, all of them are happy. We can also write it this way, right? By just replacing all those bonds or electron pairs that are bonded with a single line. And in organic chemistry, this is predominantly the way we write it out here. So you'll see this a lot and you've probably seen diagrams like this when you look at like the structures of different carbohydrates or something like that. They typically will write it this way with the lines illustrating the bonds. Okay. And the central atom would be what in this case?
The central atom.
Right. In this case, carbon is a central atom, right? And the central atom in the formula has the least number of atoms. 2 bonding electrons between carbon and hydrogen can be drawn as a line, like we just said, and then the central atom is the atom in the formula with the least number of atoms to itself, in a sense, right? So this is carbon as the central molecule. Okay, and you'll see, again, organic chemistry really goes into this a lot. Carbon often acts as a central atom in the molecular structures. Okay, so here's again some more examples. The electron dot formulas for the common molecules such as methane, ammonia, and water. This is the first slide that we looked at too, so you can see that again. Here's the Lewis structures with the pairs shown with the dots, and then the lone pairs shown as dots here in the next set with the bonded pairs shown as lines, which is a little bit simpler and a little easier to kind of grasp quickly. And then these 3-dimensional models we'll understand a little bit better too once you've actually had a chance to play with the 3-dimensional model kits, but that's one way to depict them as well. Okay. Any questions so far? We'll keep going here. All right. So we want to draw the Lewis structure for phosphorus trichloride, which is used again for as pesticides and flame retardants and such. So who would like to give that a shot? Who has their annotate working okay?
I can if nobody else wants to.
Nobody's brave. Go ahead, Lexi. So what's our first symbol going to be? or maybe I should ask first, what will our central atom be? It's the one with the smallest valence number relative to what it would need, right? Phosphorus will be
Phosphorus.
our central atom, because phosphorus is in group 5, and so it has 5 outer electrons, but chloride is in group 7, so it has 7 outer electrons, right? So phosphorus will be our central atom. And it will, go ahead and draw the dots around it first. And we'll draw the dot structures first. So go ahead and draw the 5 electrons around it. And remember, you put one on each side, and then you double up on one of them. Good.
You could open my door if you want. Oh, I'm sorry. I didn't.
You're good. It's okay. Good. So we've got a pair, and we got 3 that could share, right? And then chloride, each of them have 7. So somebody who wants to do some counting, how many electrons do we have to start with? How many valence electrons do we have going into this problem? So you'd add up the ones that phosphorus has and then all of the ones coming from the 3 chlorides. How many would we have altogether?
26.
26? Let's see. Yeah, we'd have 7 times 3 plus 5. Yes, 26. So we'd have to have 26 when we're done here too, right? And we want to make sure we have all 26 distributed around our molecule. Good. Excellent. Good. And then one more there. Perfect. Excellent. Okay, go ahead and circle the ones that are going to be the pairs that are being shared, or the bonds. Very good. So we have 3 bonds. Aiden, do you want to draw this with the lines instead of the dots for those shared pairs now?
Yeah, I can.
So if you want to just erase where the pairs are and put the lines in, that's fine too. So you don't have to rewrite the whole thing.
I can erase my.
Oh, sure, you can do that too. All right, so go ahead and put the lines in where they need to go, Aiden. Perfect. Perfect. So again, our central atom is phosphorus because it was bringing the fewest electrons to the equation to begin with, right? And then the others are going to form bonds around it until we've used up all of our electrons and we've bonded so that everybody has 8. So the other way to check yourself is to make sure that as you go around each individual atom, make sure they all have 8, right? So this chloride has 1, 2 here, 2 here, 2 here, 2 here, so it has 8, right? This chloride, the same thing. There's a total of 8. This one also has the 6 in the lone pairs and the 2 in the bonded pair, so it has 8. And the phosphorus has 6 in pairs and 2 extra here, so they all have 8. Right? So that's one way to double check yourself when you're done. Just make sure you have 8 around each one. And when you get into more and more complicated molecules, it's kind of a good idea to do that. All right, so we'll see what they say here. Of course, first of all, you want to determine the arrangement. So which one is the central atom? We did that. Then you're going to figure out how many valence electrons they each had, which we did. Phosphorus here has the 5, chlorine has 7, and we get our total number of electrons, which is a really important step, like we said, 26 electrons. Then step 3, we're going to put the central atom there, put the bonds in. We did it the other way to show the dots first, but you could put the bonds first. Then you could take the electrons you have left over and distribute them around the molecule. So in this case, we have 6 in our bonds, so we'd still have 20 left, and we could distribute them, putting 2 around each of the sides where they don't have a bond. That would be one method of doing it. Any question on how you do that? Okay. All right, then again, like I said, you put the remaining electrons around here so that they all have 8, and you have those 20 are distributed as needed around the chlorines and the 2 on the phosphorus here, so that everybody's got 8. Okay, so that was that one. Now we're going to move on and talk about double bonds and triple bonds. So just when we think we've got it figured out, we have to throw in a monkey wrench and make it more complicated. Let's see. Shanae, do you want to read us this slide?
Yeah. Double and triple bonds. A double bond occurs when atoms share two pairs of electrons. Forms when there are not enough electrons to complete octets. A triple bond occurs when atoms share three pairs of electrons. Form when there are not enough electrons to complete octet.
Octets, right. Very good. Okay, so as you can see here, in the examples they gave us, if we started off with oxygen, how many electrons does oxygen have on its outer valence?
6.
6 from its group number, right? Carbon has how many?
4.
4. And the other oxygen has 6 here, right? So each of them want 8, so we have to figure out how they can share to get that, right? And we know that carbon's going to be our central molecule because...
The least electrons.
Right, it has the least to bring to the table, right? Okay, so we're going to figure out how many electrons we have all together, which is going to be what?
16.
16. Very good. And then we're going to figure out how to distribute them, right? So when we do put them around our, in a dot structure here in pairs like this, we can see that we can share 2 here and 2 here, 2 here and 2 here, and then we have exactly 16 electrons, and we have them all with 8 around them, right? So sometimes you have to play with it a little bit just to figure out how to get this arrangement right, because you know you only have the 16 to work with, right? And you have to make sure you're distributing 8 around each one of these. Okay, so there's sometimes only one way to do that. In fact, most of the time there's really only one way to do that, right? So it's almost one of those logic games in this case. So when you do it this way, though, you have 1, 2, 3, 4, 5, 6, 7, 8 around this oxygen, right? And you have 1, 2, 3, 4, 5, 6, 7, 8 around the carbon. And you have 1, 2, 3, 4, 5, 6, 7, 8 around this oxygen, right? So when you write it out with the lines, now you can see that you'll have a double bond between the oxygen and the carbon on both sides. How is that riding with everybody?
Okay.
Making sense? Okay. It's nice when you have good examples like this. Sometimes they're a little bit trickier, but we'll keep going. All right, so triple bonds now. So how many electrons do we have in the hydrogen as it's coming into the molecule here? How many does it start with?
2.
1.
Hydrogen's going to have 1, right? Carbon's going to have how many?
4.
4. Nitrogen's going to have how many?
5.
5, right? So how many do we have here?
10.
We have 10 electrons, right? And we got to figure out how to share these 10 electrons so that hydrogen gets 2, carbon gets 8, and nitrogen gets 8.
Okay.
Making sense?
Yeah.
Okay. So it's kind of like that game where everybody holds hands and then they twist themselves up kind of thing. It's a little bit of, mix and match until you can figure out how to get everybody happy, right? So when we do it this way, we have a double bond between the hydrogen and the carbon on one side, right? And hydrogen has the 2 at once, right? We need 6 more for the carbon, so we give it 3 bonding pairs here. Now it has 8, right? Because there's 6 here and 2 here. There's 8 electrons going around the carbon. And nitrogen is sharing those 6 as well with the carbon, and it has 2 left over, and so it has 8 as well. And how did we know which one was the central atom again coming into this? I forgot to ask that question first. Why would we put carbon in the middle?
It's the least amount of atoms.
Right. I mean, hydrogen only had 1, right? So technically it was the least, but because hydrogen only needs 2, carbon is actually bringing less to the table in terms of how many it has toward its valence of 8, right? So carbon's going to be the central atom. Okay, and that's how we can decide that we have the 3 pairs going between the carbon and the nitrogen and the 1 pair going to the hydrogen from the carbon, because it's the central one. Okay, So you can see how they each get 8 and they're all happy when we set it up as a triple bond. Okay. Any questions there so far?
Written out, will carbon be like, what would that be? Like, will carbon be in the middle? Right? Just, do you get what I'm saying?
Yeah, carbon is often in the middle for most of the examples that you're going to see, simply because carbon being in group 4 usually comes in with the fewest electrons for a lot of these covalent bonds, because most of the other non-metal atoms that we're going to be dealing with tend to be in groups 5, 6, or 7, so they have more, right, coming in. So carbon is often the central one. But always think it through, because sometimes there's exceptions, right? And so you want to make sure that you don't confuse yourself. Always go through the process of figuring out, okay, other than hydrogen, which one's coming in with the fewest electrons to share, and we'll make that one the central atom. Okay. Yeah, there was one. Oh, I know what I wanted to show you back quickly. What was that? Yeah, this table here is useful to have as a reference for this, again, because we know carbon has to have 4 bonds. And so when we have those 3 triple bonds, nitrogen can have up to 3. So nitrogen is in, just when you see a nitrogen in a molecule, you can kind of think to yourself, it's not always the case, right? But you can think to yourself, well, I can have up to 3 bonds of the nitrogen. So when there's triple bonds, a lot of times nitrogen's involved in them, right? Same with phosphorus. And oxygen's only going to have 2, right? So it helps to have this table in mind as well, because they won't usually have extra bonded pairs more than that, right? So this is also part of the reason why carbon is in the middle, because it has the opportunity to bond with 4 other things, right? Whereas the other molecules are I don't know, they tend to be more like on the fringe, because they can only have up to 1 or 2 bonds. Except for nitrogen, of course, which can have 3. But does it make sense?
Yeah.
Okay. So that table is a nice reference to have handy when you're working on these. Oops, I went too far here. Okay, so we talked about the double bonds and the triple bonds. And it definitely stop me if there's anything that you want to go back to. But so now that we've got, again, we finally figured out, we've gotten something figured out. There's always some exceptions, right? So the exceptions to the octet rule that are useful to remember here. Let's see, who would like to read this in a very authoritative way? Aiden, can you read us this one?
The whole thing?
Yes, please.
Okay, cool. I was confused with the highlighted part.
Oh, sorry. The highlight was just I think of highlights as kind of like my way of making extra notes, like really, make sure that you if you have a photographic memory, make sure you take a picture of this in your mind, or like pay attention to it extra. But yeah, go ahead.
While the octet rule is useful, there are exceptions. Hydrogen requires 2 electrons to form a noble gas arrangement. Nonmetals, phosphorus, sulfur, chlorine, bromine, and iodine can form compounds with 10 or 12 valence electrons. The S atom, sulfur, sorry, the sulfur atom has an octet in many compounds, but in SF6, there are 12 valence electrons, or 6 bonds to the sulfur atom.
Right. So sulfur hexafluoride is an exception, right? Yeah. So we don't deal with the exceptions too frequently in this class, so don't stress about it too much. But be aware that if you were to go on into more advanced chemistry and stuff, some of the rules that we're learning and we're using quite frequently in class now may be broken a little bit as you get into more and more advanced chemistry. Okay, so you'll see maybe a couple of these in our class. You won't see them very frequently, but we should be aware of them. Again, the universe isn't always as cut and dried as we'd like. Okay, so you can see how those are arranged here with the bromine trichloride, and the sulfur hexafluoride. Okay. All right, and that's it for that section. I think the next one is fairly short as well, so I'll jump into the next section if everybody's good with that. Are we okay for that?
Yes.
Okay. Let me make sure I'm jumping into the right one. That was 6, so we need 7. Okay. So back to our old friend electronegativity. This is going to help us understand how the molecules behave, particularly for their chemical properties. So electronegativity, remember that? What did it mean? Our table here will kind of give you a little bit of help. What does the electronegativity mean? It's getting too late to ask a mean question like that, isn't it? Electronegativity was how hard the nucleus kind of hangs onto its electrons, right? Which means a little bit about how far they're out from the center of the atom, right? So the further they are away from the center of the atom, the easier it is for them to be lost in the case of metallic substances here. And in the case of nonmetals, we usually have them closer to the nucleus, and so we usually tend to steal electrons from other atoms. So the electronegativity increases as we move to the right of the periodic table, right? So fluorine up here is the most electronegative of all the elements because the noble gases are not electronegative because they are so balanced and happy and so antisocial, right? But the rest of them have electronegativity issues, and the metals, it's decreasing as you go from top to bottom, right? And increasing as you go from left to right. Okay. So as you can see these little numbers here on this table, you can take a screenshot if you want of these. You're going to be seeing these a lot. These are the actual measures of those negativities. Okay. And you can see that it generally follows the rule of decreasing as it goes down and generally follows the rule of increasing as it goes left to right. But there's, like little, they're not exactly the same for each step up in the groups or anything. So you need to have a reference table like this to actually get the exact negativity measures for each of these elements. Okay. So you might want to take a screenshot of this. I have another table showing them in a little bit too. You should have a copy of it in your book as well. Okay, so electronegativity is going to help determine the polarity of the bonds. Again, thinking like a magnet with, positives and negatives, charges. The polarity of these individual molecules is going to be determined by the electronegativity of the atoms going into them. Let's see. Lexi, do you want to read us this slide?
Yes. The electronegativity of an atom is its ability to attract the shared electrons in a chemical bond. It increases left to right going across a period on the periodic table. It decreases going down a group on the periodic table. It is high for the nonmetals with fluorine as the highest, and it is low for the metals.
Excellent. So kind of a general rule of thumb for what negativity is. And it's easy to see that all of these work out when you look at that table that we just had in the previous slide. And again, here in a bigger version of it, you can see, again, increasing as it goes toward fluoride up here and decreasing as it goes down toward the larger and larger atomic sizes in the metals as well. Okay. So what is the most electronegative element? Or has the highest electronegativity?
Fluorine.
Yes, fluorine. Fluorine hangs onto its electrons very tenaciously. Okay. Esther, can you read us this slide?
Yes. The difference in electronegativity of bonding atoms can be used to predict the polarity of the bond. In the hydrogen molecule electrons, are shared equally, and the bonds in non-polar. In
This
the
is hydrochloride. Yeah, this is called hydrochloride.
Okay.
Yeah.
Molecule electrons are shared unequally, and the bond is polar.
So you can see in the pictures here, right? A dihydrogen bond, or one where there's two hydrogens, each of these hydrogens has exactly the same electronegativity, and so they're going to hang on, like if you imagine like a tug-of-war game, right? They're each putting exactly the same amount of pull on these electrons, or they're sharing them exactly equally. So there's at no point as these electrons are zooming around these two hydrogens are they building up a charge in any one location, right? It's balanced, and so there's no electronegativity or no net electronegativity. Whereas here with the chloride and the hydrogen, chloride is really strongly electronegative compared to the hydrogen, right? So it is going to hog the electrons like nobody's business. And it's going to mean that this part of the molecule where the chlorine is going to have a slightly negative charge. And we show that with this little delta symbol and the negative, right? So this part of the molecule is kind of like the negative end of the magnet. And there, where the hydrogen is, it's not going to get the electron very often. And so it's going to have this little delta symbol and a little positive. That's kind of how we show these electronegativity charges. They're very, very small charges, but when you're down at the molecular level like this, it makes a big difference in how they react toward each other. This is a little bit positive. This is going to be a little bit more negative. It's kind of like they're sharing custody of these electrons, but hydrogen only gets them at Christmas and New Year's, whereas chlorine gets it the rest of the year, kind of thing, right? So it's a little bit more negative on that side of the molecule.
I like the analogy.
I don't know, maybe I think of it weirdly, but yeah, that makes sense to me anyhow. All right. Okay, so now we have different terms for all these different types of bonds. So a nonpolar covalent bond occurs when you have two nonmetals, right? And they have equal electronegativity so that they share their electrons equally. They have equal rights to the kids, so to speak, right? They share the electrons perfectly equally, and the bonds don't create any more negative parts of the molecule, okay? There has to be a very small electronegativity difference between the atoms. So this is a rule that you can use between 0.0 and 0.4. And again, you want to look at the table that we just had that showed the electronegativity for each of the elements. You can subtract the electronegativity just like you would any other kind of mathematical formula here. So for nitrogen, each of them have an electronegativity of 3. So if they cancel each other out, you have a nonpolar covalent bond. For chlorine and bromine, they're also really, really close. So you only have a 0.2 difference, and so it's still a nonpolar covalent bond. For hydrogen and silicon here, they're pretty close as well. 2.1 and 1.8, close, only 0.3 difference. You still have a nonpolar covalent bond. In other words, they have fairly equal custody of their electrons. Now, polar covalent bonds are a little bit different. Sinead, do you want to read us this one?
Yeah. Polar covalent bonds. A polar covalent bonds occur when nonmetal atoms. It is an unequal sharing of electrons, has a moderate electronegativity difference from 0.5 to 1.8.
Okay. So again, this is the rule of thumb that you want to kind of make note of, the 0.5 to 1.8. And again, oxygen and chloride, if you look at the table, oxygen has 3.5 as its negativity and chloride has 3, right? So there's only a 0.5 difference. So it's enough of a difference that you're going to have the molecules slightly unequal, like chlorine is going to hog the electrons more than the oxygen, and that part of the molecule is going to be a little bit more negative, right? And then here between chlorine and carbon, carbon is only 2.5 and chlorine is 3, so there's going to be a 0.5 difference, and the chloride again is going to be the hog. It's going to have more custody of the electrons. It's going to have them more of the time. On oxygen and sulfur, again, there's a difference of 1 here in their electronegativity, and so the sulfur in this case is going to be hogging the electrons a little bit more. No, I take that back. This one is the one that has a higher electronegativity, which is backwards in terms of where they are on the periodic table, but that occurs sometimes too. So you need to go back to the table always and look at the actual numbers for their electronegativity. And I'm just going to back it up so I can show you that again. really quickly. So this table here is a really nice one. So here you can see where oxygen is 3.5, sulfur is 2.5, right? And so even though they're in the same group, because oxygen's a little closer to fluoride here in terms of higher up, it's going to hog the electrons more than sulfur. Okay. And again, look at the numbers. Okay. There we go. Okay. So, oh, back again. If you guys want a screenshot of this, please take it. This is a good way to have all of those electronegativities, which I'm not sure it's in your book. I know they have a partial table of electronegativities in the book, but I don't think they have the whole thing. Correct me if I'm wrong. I know the slides didn't, but I had to add this one in.
It's not in the book.
Okay.
Yeah, it's not in the book.
So go ahead and grab a screenshot of this if you want, or I mean, obviously you can always Google it, but it's kind of, I liked this one. It was fairly easy to see. And again, you can see like the noble gases off to the right here, they don't really count because they don't have the issues with electronegativity because they don't bond with other elements. Okay, holler if I have missed you and you haven't gotten one, but we can always go back and let you get a screenshot. All right, so moving on to different types of bonds that relates to their negative or their electronegativity characteristics. We have polar covalent bonds, and there's different types. Okay, so let's see, who hasn't read in a minute? Alan, can you read us this one?
A polar covalent band becomes a more polar as a difference in electronegativity increase the separation of the charge in a polar band is called dipole.
Dipole?
Dipole.
Mhm.
The positive and negative ends of dipole are
Sorry.
located by using the lowercase Greek letter or delta, which a positive or a negative charge, and an arrow that points from the positive to the negative ends of the dipole.
Mhm. So if you're going to write the symbol out and you're trying to illustrate the negativity of it, this is how you'd write that. So this would be a carbon and an oxygen, and this isn't necessarily showing the fact that there's only one bond here, but in the molecule, the carbon would have less of a pull on the electrons. The oxygen would hog them a little bit, and so its end of the molecule would be more negatively charged, and the carbon would be more positively charged. And in the case of nitric oxide here, what do we see? Who's hogging the electrons?
Oxygen.
Oxygen is, right? Nitrogen is not. Okay, and again, if you look at the electronegativity, oxygen is 3.5 and nitrogen is 3, so there's a difference of 0.5, which is enough to make it a little bit polar. Okay, and then here's chlorine and fluoride, right? They're pretty close, right? Chlorine is 3, but fluoride is 4. They're very close in the periodic table, but fluoride is such a hog of electrons that it's going to take custody of those electrons a lot more of the time and make its end of the molecule more negative. And as you can imagine, if you are, if you've ever gone to those museums where they have those like rock displays where you have like just plain pebbles, and then you go to the one where they have the little magnetic rocks, they react, these small particles, whether they're magnetized or not, makes a big difference in how they react around each other, right? If you have a little bin of magnets, they're all going to stick together, right? If they have the right sides of them, positives and negatives, attracting, etc., right? Whereas if you have just a bunch of pebbles, they're not going to be sticking to each other at all, right? So this is the difference between non-polar molecules in solution and polar molecules. They behave very differently around each other. So polar covalent bonds have these dipoles, or like little miniature magnets that they form, and this is how we illustrate that. All right, now kind of going back again because we're trying to compare how ionic bonds relate to these other types of bonds. Josita, can you read us this one?
Yes, ionic bonds. An ionic bond occurs between metal and nonmetal ions as a result of electron transfer. has a large electronegativity difference greater than 1.8.
Very good. So the 0.5 to 1.8, that makes a polar covalent bond, right? And then if we go beyond that, we're going to end up with ionic bonds, where one of those atoms is going to completely take custody of all the electrons and never give any visitation rights, let's say, to the other atom. Okay, so that's an example when we have a metal and a nonmetal frequently. So chlorine and potassium here. And usually we would put this in the other order and call it potassium chloride, but we're just going to show here the electronegativity differences. Is 2.2 is the difference, right? So it's definitely going to be an ionic bond. And then here, if you look at the nitrogen and sodium, right? Sodium has an electronegativity of what?
0.9.
0.9, right? And nitrogen has an electronegativity of
3.
3, right? So there's a big difference here, right? And that difference means that you're going to have an ionic bond. In other words, nitrogen is not going to give sodium custody of any electrons ever, essentially. And so it's going to be very, very negative on the side of the molecule where the nitrogen is. All right, so a quick summary here. Sinead, do you mind reading us this?
Summary, variance, and bonding. The difference in electronegativity values for two atoms can be used to predict the type of chemical bond. If the electronegativity difference is between 0 and 0.4, the bond is nonpolar covalent. Between 0.5 and 1.8, the bond is polar covalent. Greater than 1.8, the bond is ionic and the electrons are considered transferred. Between 1.8 and 2.0 can be either polar covalent or ionic. It depends on the elements involved in the bond, non-metal, metal, non-metal, ionic, two non-metals covalent.
Right, so again, if you have two nonmetals, except for the case of ammonia, usually they have covalent bonds, although there may be a fairly large difference in their electronegativity. We still call it a covalent bond if it is between this 1.8 and 2, right? And I'm trying to think. I don't know that there's any of the nonmetals that could combine to have any greater difference between more than 2. I don't think that's even possible. Yeah, looking at those, that's not possible to even have anything that would have a greater electronegativity difference if they were both nonmetals. But for the metal nonmetals, it is possible to have greater than 2 in terms of difference in their electronegativity. Okay, so any questions on this? Again, the nonpolar covalent bonds, think of them as like these molecules have no magnetism at all to them. They're like those pebbles in the bin. They don't stick to each other at all. If they start to be polar, they're like little magnets, right? Some of them are a little weaker magnets than others, but they are going to start sticking to each other because they are a little bit more or less magnetic, right? So the molecules that have these polar covalent bonds are going to have different chemical properties when we put them together, right? And then once they're in ionic bonds or very, very highly electronegative differences here, like between the 1.8 and 2 for the non-metal covalents, they're really going to be like very strong magnets. And they're going to be sticking together a lot if you put them in a solution together. Okay? All right. Any questions? All right. So here's another way of kind of picturing that, which I think is really useful. Here's the non-polar. And we imagine that you have a nucleus in here and a nucleus in here. And this purple thing is like the electron clouds, and you can see it's very nice, it's equal, very, I'm sorry if this is not a very good visual, but they're very equal in terms of how close they are together, right? And then here with the polar covalent bonds, if you have the little nuclei in there, all right, this one here on this side is not getting the kids very often, right? It's got limited visitation rights, whereas this side here is hogging those electrons, right? So it has a relatively high electronegativity compared to the other side. And so again, it's between 0.5 and 1.8 is the difference between these two molecules, or two atoms, sorry, and they're not going to equally share their electrons. So you have the cloud arrangement here is going to look a little different, and this side's going to be more positive, this side's going to be more negative. Then when we get all the way over to the ionic bonds, this is the metal here, and this is the non-metal, right? Put their metal, non-metal on them there. And so the metal is going to give up all rights to its electrons, or its valence electrons anyway, right? And it's going to give them to the non-metal. So the non-metal is going to definitely be negative, and the ionic or metallic side of things is going to be very positive, okay? And so we don't necessarily use the delta there because it's not like a relative thing. They are negative and they're positive. There's not a nuance. Like with these, there is some sharing of the electrons, okay? Any questions on that? Again, this is kind of just something you got to memorize in terms of the actual parameters. You're going to want to have that written down somewhere, because that's the kind of thing that, for sure, with a test on Pearson, they would definitely want you to be able to use those parameters to decide which bond you're dealing with, nonpolar, polar, or ionic. Okay. How are we feeling?
Good.
Good. All right, keep going here then. All right, so again, this is just showing some of the formulas that we've talked about and how the bonds are, and then the electronegativity differences, and then the type of bonds. So just kind of a recap of what we've just talked about. So for sodium chloride on there, what is the electronegativity difference for sodium chloride?
2.1.
2.1, and it is an ionic bond then, right? Okay, what about hydrogen bromide, hydrogen bromide.
Polar covalent.
And what's the electronegativity difference?
0.7.
0.7. Very good. Absolutely perfect. Okay. And then magnesium oxide.
2.3.
2.3. And we know that's going to be ionic because magnesium is a metal, right? And oxygen is a non-metal, so we know it's going to be ionic. Very good. But then for dihydrogen, what do we have there?
0.
0 electronegativity difference. And what kind of bond?
Non-polar covalent.
Perfect. Very good. Everybody feel like they're kind of getting this? We don't have to worry about it too much? Yes. Good. All right, so we'll do some checks here. So using the electronegativity difference, we want to be able to identify the type of bond, whether it's nonpolar covalent, polar covalent, or ionic, between the following. So, Shanae, what is A? This is what? K is?
Potassium.
Potassium, very good. And this is?
Nitrogen.
Nitrogen, very good. So what are they probably going to be doing here with this bond? What kind of bond is this?
Let's see.
I'll clear my mess.
Ionic?
It'll be ionic. Very good. Yes, because why? Sorry.
It was my fault, my bad.
Like, I did not have enough coffee for this, right?
I forgot.
It's okay. Somebody else want to jump in and help her out there? Why is this an ionic bond?
Because it's a
Potassium
metal.
is metal.
Right. Metal and non-metal. Perfect. Exactly. All right. Let's see who is hiding on my screen here. Is Aubrey here? I haven't seen her in a bit. She was starting off, and I think her stuff must have got knocked off. Lexi, can you give me B?
Yes, I think it is not, or polar covalent.
A polar covalent. Why would we think that?
The difference is 0.5, so it makes it just enough to be polar covalent.
Beautiful. Yes. Excellent. Okay. Josita, C.
That's 0. So it is Non-polar covalent.
Non-polar covalent. Very good. Excellent. And D. Aiden, you're the only one left on my screen here. What is D?
Could be covalent, but yeah.
Hydrogen has an electronegativity of 2.1. Chloride has an electronegativity of 3. So the difference is
It'd be a polar covalent.
0.9, right? So it is polar and covalent. Very good. I'm putting PC here, but I guess they were just using a P, but okay. All right, let's check ourselves. Very good. Ionic, polar covalent, non-polar covalent, and polar covalent. Very good. So far, it's clear enough for everybody?
Yes.
All right, so let's take a break here. Is there some internet problems? I feel like we've just lost. Oh, there we go. Now my button's working. There are more people on here. I'm so sorry. They just stopped working for me for a second. I thought I'd lost a bunch of people, but it looks like everybody's actually here. Okay, very good. Let's take a break and come back around 9 o'clock. I think we got time for like one more section, if that's okay. So see you back at 9 o'clock. Or thereabouts. Take a few more minutes if you need to. All kinds of stuff, yeah.
Oh, okay.
Yeah. Okay. So, this is the fun part. I wanted to make sure we get through this section because for everybody who's in town, I will deliver, if I can, tomorrow. Hopefully, I'll be able to coordinate it and be able to get you a kit if you don't have one. So I will need to make sure that you need one. One of the little plastic modeling kits, because we have, like I said, we have tons of them at the lab. So I'll be able to bring those to you to play with this, because I just feel like that if you don't even get this part of the class, it'll be a real shame. So I'm going to make sure you have those to play with. And then for those of you who aren't in town and maybe don't have access to this, let me know. We'll come up with something. You can use toothpicks and marshmallows. You can be pretty creative, or if you have, different art supplies or something, you can have some extra fun with it too. I want you to all have a chance to give it a try. And if you don't have the actual kit, I won't be as hard on you if your angles aren't right or something like that on your molecules, because that's a lot harder to do when you're working with stuff that's not designed for it. But I want you all to have the chance of handling a 3D concept here in terms of these molecules. Okay, so starting with methane, and methane's a fun one again, because if you move on to organic chemistry, you're going to be very familiar with it. You have carbon as the central atom, because again, it's only got 4 electrons to bring to the table, and hydrogen is closer to having its valence filled, because it has 1 and it only needs 1, right? So there's these different ways of writing it out. We could have the Lewis structure here. This is not the Lewis dot, but this is the Lewis structure, and we would put dots there sometimes, right? But in this case, we're just putting a line to show 2 electrons per line. Right, so how many electrons are around the carbon then?
12 or 8.
8, right? Because each one of these is showing us that there's 2. 1 was from the carbon, 1 is from the hydrogen. So there's exactly 8. And then each of the hydrogens gets to share 1 with the carbon and keep its own. So each of them has 2, so everybody's happy. And then in a 3-dimensional shape here, which we're going to call a tetrahedral, tetra meaning 4-sided, 3-dimensional shape, tetrahedral, we have, because of the polarity of the molecules, right? These hydrogen groups are what would they be slightly more? This is a polar bond.
Electronegative.
They would be slightly more positive, right? Because they have fewer electrons. So because they are slightly more positive, they're going to want to repel each other, like how 2 like charges repel, right? So they're going to try to keep their distance from each other as equal as possible. Okay? So all these hydrogens are going to spread themselves out around the oxygen so they each get an equal amount of real estate, essentially. and that's how they get this shape. That's how their geometry works out. So the tetrahedral shape here, you can see there'll be about 109 degrees between each of them in order so that they can really spread out. Okay, and then this is another way we can draw it with this wedge notation here. These symbolize that some are pointing toward us, some are pointing away from us, and some of them are in the same plane. So let me highlight that a little bit better. So this one is pointing toward us, this is pointing away from us, and these two are in the same plane. So we can create this three-dimensional shape with a flat diagram. Okay, so that's just the example for methane, and in reality, this is not a polar covalent bond, I don't believe, but the idea is that they want to stay as far away from each other as possible. So even if you are dealing with covalent bonds, the hydrogens are slightly more positive, and even that little bit makes them want to spread out from each other. Okay, so we want to be able to understanding the types of negative electronegativity and the polarity of the molecules and all that. We want to be able to now predict the way they've shared their electrons and everything. We can actually deduce what their three-dimensional shape will be, which I think is pretty cool. So here goes. We'll deep dive into this. The way we do that is through this valence shell electron pair repulsion theory, or VESPA. So Aubrey, are you up for reading this, or do you need to be off right now? Okay, it's okay.
I can read it.
Oh, okay, go ahead.
Valence shell electron pair repulsion.
Sorry about that. Go ahead.
Repulsion therapy. Describe the orientation of electron groups around the central atom. States that electron groups are arranged as far apart as possible around the central atom. States that the specific shape of the molecule is determined by the number of atoms attached to the central atom.
Okay. So when we know all of these things, which we do, right, from understanding what we've learned so far, we're going to be able to figure out how to name them and give them their shapes. Okay? Okay. Esther, can you read us this one?
Sure. Any molecule of carbon
dioxide?
Carbon dioxide, two bond electron groups are placed around the central atom, carbon. Repulsion is minimized by placing the two groups of opposite sides of the carbon atom, given the linear arrangement of bond angles of 180. The shape with two electron groups around the central atom is linear.
So again, we kind of skipped a few steps in this one, but the oxygen has how many valence electrons when it comes to the equation here? Oxygen has how many?
6.
6. Carbon has 4, and the other oxygen has 6. So we have those 16 electrons, right? And we did this one before, but we have to set them up with double bonds so that all of them get their valence. And in order to do that, that's the arrangement we got to give it, right? So the carbon has 4 here, and carbon has 8 with the two double bonds, right? And each of the oxygens also have 8. So we distribute the 16 electrons in such a way that everybody gets their share. And when we do that, we're going to see that we have this arrangement with the two double bonds. And following the rules of the repulsion theory here, we can see that they're going to want to be as far apart from each other as possible, the two oxygens. And so there's no way to get further from each other than the opposite sides of the carbon, right? So you're going to end up with this shape here. So that's a nice simple one to start with, and it makes sense, I hope. We all following there? Okay.
Yeah.
All right, because it gets a little bit more fun as we go. Now we're going to look at formaldehyde. Again, this would be something you'd see in organic chemistry quite a bit as well. So now you have a central carbon, right? Because again, oxygen has 6 electrons it's bringing, carbon has 4, hydrogen has 1 each, and carbon's going to end up being the central atom because it's bringing the fewest, and it can form the most bonds, right? So hydrogen can form 1 bond on either side of this carbon, and carbon has 1 more that it can share, and it only has 1 other, entity to share with, so it's going to share with the oxygen, and it's going to form a double bond. That way carbon has how many electrons around it? If we count the 2 for each of the lines?
6.
2 for each of the lines. So we're going to actually have 8, right? Because there's a double bond here. So there's 2, 4, 6, 8, right? So carbon's got 8. How many does oxygen have? It's got these 2 lone pairs, and then it's got 2 for each of the lines. So it has
8.
8 as well. And each of the hydrogens has
1,
2.
2 because it's got a bonded pair there with it's sharing 1 with the carbon, right? So they each have a full valence. So they're all happy. And how many electrons total? We started off with 6 from the carbon, 2 from the hydrogens, and how many from the oxygens? We had 3 times 6, right? Because there's 3 of them. So we have 18 from the hydrogens, 4 from the carbons. We got 22 plus 2. We got 24 electrons to begin with, right? Do we still have 24 here now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Did I count that wrong? 3 times 6 should give us 18. Oh, just a second. I'm looking at there's not 3 oxygens here. Oh my goodness. Sorry, guys. They are not using the same illustration in their picture that they're talking about here. So this is H2CO. Right? So there would only be, forget that mess there. We'd have 2 and 4, 8 and 6. We'd have 14 electrons. Sorry guys, my coffee is dwindling here too. So, and then if we add them all up, we have 1, 2, 3, 4, 5, 6, 7, 8 here around the oxygen, and then 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, did I still count that wrong? 6 here, 4 here. Oh yeah, I did count that wrong. That is 12 to begin with. Okay guys, my math is not working. Somebody's gonna have to fire me here. So, my goal was to count the electrons coming into the equation, and this was the wrong molecule for this. But if you have H2CO, which is what this is showing us here, you would have how many electrons altogether
2
coming
plus
in?
6 plus 8.
12, right? 6 here, 4 here, and 2 from the hydrogens. So we'd have 12. I was counting wrong about 3 times there. I'm so sorry. 12 electrons, and there's 12 electrons when we disperse them around this molecule as well, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in the Lewis structure, right? So moving on to the next way to look at this, though, we know that they're going to want to, each of these entities around the central atom are going to want to spread out and get as much real estate as they can. So they're gonna do so, and when they do that, they're gonna spread themselves out like this, right? So that you have, it's like 109 degrees between them here, right? They're gonna spread out as far, sorry, 120. All I'd have to do is look a little further on my thing here, right? So this is 120 degrees between each of these. And you can see that here in the trigonal plane or three-dimensional picture here as well, right? So the way we know what the shape is it's planar, because within the plane they can get as far apart as they need to from each other, because there's only these 3 things, and they can stay in the same plane and move away from each other and be okay, right? In terms of distance apart. And there's just 3 of them, so we call it a trigonal planar electron group geometry here. Trigonal planar shape here. Are we losing anybody, or is this making sense still? It takes a little bit of 3D imagination, which is why I really want you guys to have a chance to play with it three-dimensionally, because if you have, if these weren't all in the same plane, they'd actually get closer to one another if you were to try to shift them out of that plane around the central carbon. So they have to be planar and trigonal because of the three different things sticking out from the carbon. Okay? So again, having a three-dimensional thing to play with would help make this more clear, I'm sure. But are we following along so far?
Yep.
Okay, thank you, Aiden. All right. So our next molecule is sulfur what? What do we name these again?
Dioxide.
Sulfur dioxide. Very good, yes. And I keep bumping my... There we go. Okay, so sulfur dioxide. And how many electrons do we have as we start in here? Sulfur has how many?
6.
Oxygen has?
6.
And there's 2 of them, so we have
2.
Yeah. 3 sets of 6, or we have 18 electrons going into our scenario here. So we're going to write them out here. We're going to put sulfur is going to be our central here because we have the 2 oxygens. And even though they all have 6s they're coming in, because there's only one of the sulfur, it's going to end up being in the middle. Okay? So oxygen, and as we distribute these electrons, we're going to start off with putting in the bond. So we'll put one bond between the sulfur, one bond in each oxygen, and then try to distribute our electrons. As we do that, they're giving us the answer, but you'd end up needing a second double bond in order to get them all to fit in, right? So we should have 18 electrons here now. 1, 2, 3, 4, 5, 6, 7, 8 around this molecule. Then the same 2 here, so we have 8, 9, 10, 11, 12, 13, 14. And if we count, there's 8 around the sulfur as well, because it has 4 pairs around it, right? And so it's got all its valence electrons. And then this last oxygen, how many do we have left to work with now? We've counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have how many left? We only have 4 more to put around, right? And so we can only distribute these last 4 around this oxygen like this. And it's going to have 8 because we created a second bond here with the sulfur. So it's going to have all 8, and we've used up exactly 18 electrons. So this is the configuration. Again, you might have to play with it a few times to be able to make sure you got this right, but you'd have to put in that double bond in order to get only 18 electrons and make sure that all 3 of these atoms have a valence of 8. Okay, so we know that this is going to be our shape here. And because there's a lone pair on the central atom, get my little mouse back, there's this lone pair around the central atom, it also has an electronegativity repulsive force. Okay, so we can't just leave this in a nice straight line like this when we're trying to look at what the three-dimensional shape is. These guys want their real estate too. Okay, so they're going to push these other groups out to the side, and we're going to end up with a trigonal plane arrangement again. Okay, so a lone pair of electrons, you have to pay attention to those when you're thinking about the three-dimensional shapes. They want their space, just as if there was a whole atom there. Okay, and so you can see here that you end up with this bent shape, because even though there's nothing sticking up here, right, this is just empty space, there's 2 electrons here that take up their space because they need it too. Okay, how are we doing so far with the logic behind this?
That made sense.
Okay, so we have, again, a single bonded oxygen atom, this one here. We have a double bonded oxygen atom here, and then we have the lone pair of electrons. So we have the 3 things around the central atom, and the repulsion is minimized by placing those groups as far apart as they can get. So because there's 3 of them, they stay in the same plane. You know, if they started to move into other planes, they would get closer somehow to each other, so they have to stay in the same plane, and they have to stay 120 degrees apart. And then they're all happy, and we end up with a bent looking shape here because we don't show those lone pair electrons, and so the actual molecules of oxygen and sulfur are going to create this bent shape or angled shape for the molecule, and so we call that a bent molecule. That's the term we use for its shape. Very technical sounding. Any questions so far? Again,
No.
there's just a lot of steps to think through, but hopefully it all makes sense when you think about it. Okay, somebody make some noise if there's any problems here, because I'm hoping we're all following. All right, so now we're going to move on to our methane molecule. We have 4 electron groups, and sorry, I'm going to be losing my slide here because I forgot to click on that first. Okay, so we have a methane, which is a central carbon atom, okay, and 4 hydrogens. So there's going to be 4 groups with electrons around the central atom. So we call them 4 electron groups as we're looking at it in terms of this, this model, okay? The repulsion between all of them is going to be equal, right? They're going to want to each have as much space as they possibly can get. So if there was just 3 of them, they would have the most space possible if they stayed in the same plane and they moved 120 degrees each, right? But because there's 4, now they need to start getting into 3-dimensional spaces and go 109 degrees apart from each other. So we think of it as like if there was a little sphere and they each wanted real estate on the surface of that sphere, they would have to move into this 3-dimensional shape and stay 109 degrees apart from one another, okay? And because there's no lone pairs around our central carbon atom, there's just the hydrogens, okay? They're going to form this nice shape that we call a tetrahedral, okay? Tetra for 4, and hedral meaning it's in a 3-dimensional shape now, okay? So here's what it looks like drawn in that way. This is how we would see it if we took a picture of the little model, if we made it at home with our little sticks and balls here. And then if you use this wedge dash notation, one of them would be sticking toward you, one would be sticking away from you at 109 degrees, and then 2 of them could stay in the same plane. Okay. Any questions? I know this is trying to think 3-dimensionally, and it's late at night, so that might be a bit tricky. But how are we feeling about it so far?
Not terrible.
Okay, good, good.
It makes sense. I just have a hard time like seeing shapes in my head.
Yeah, I hear you. That's why I'm hoping I can get you guys the kits to actually play with, because it will be like, oh, aha, when you can actually hold it and see it and look at it in different angles and all that. All right, so our next example here is nitrogen trihydride, which is actually ammonia. What am I saying here? See now, look how sleepy I'm getting. So ammonia, right? And we have 3 hydrogens, and we're going to end up with 4 electron groups. And why is that? Because let's go down here to our Lewis structure. Nitrogen has how many electrons when it comes into the equation? 5, right? It's 5, right? And each of these guys brought 1, right? So we have 8 electrons altogether, right? And there's going to be 2 in each of these bonds with each of the hydrogens, right? And then there's going to be 2 left over, right? Because that only accounts for 6 of the 8 that we have. And so we're going to have a lone pair of electrons. So again, pay attention to those lone pairs. They're going to mess everything up, right? Because you could look at this and go, oh, that should be a trigonal planar shape, right? But it's not, because those electrons want the same amount of space as everybody else. Okay, so again, going back to that repulsion theory, we got to minimize each of one of them is going to have as much space as they can possibly get, right? So we're going to minimize that repulsion by placing them equally around the central atom. And so we end up with a tetrahedron shape again with that 109 degree angle because of the lone pair. So even though there's nothing sticking up here that we can really, see, we know that there's a lone pair of electrons taking up this space. Can you guys see my cursor? I keep highlighting things and I'm not sure you're actually seeing it. So this lone pair gets its space, and then we have the other 3. So it's going to be a 3-dimensional shape, not a planar shape, and there's 4 different electron groups, right? Because we have a group of electrons that's shared with each of the hydrogens and then the lone pair. So we're calling them each an electron group, even though there's there's an atom here too, but as far as this repulsion theory goes, we're looking at the electron groups. And so we end up with this tetrahedral shape, but because there's not really anything here, we call it a trigonal pyramidal shape. Okay, so it looks kind of like a little pyramid with three hydrogens as its base here. Does it make sense? We don't, since there's not actually something sticking up here, even though these electron groups are forming a tetrahedral shape, because there's nothing actually here, we're going to see a shape that looks like a trigonal pyramid in terms of the molecular shape. And then if we drew it out with the wedge dash, we'd have one in the central plane, let's say, one sticking towards us and one sticking back away from us. And we draw it out like that. And I'm not going to require you guys to do a whole lot of these wedge dash drawings unless you really like it and you find it fun. But we'll work more on these other things. I'm going to try to have you guys do some three-dimensional shapes, and definitely want you to be able to draw the Lewis structures. Okay. Okay. So far, does it make sense?
Yes.
Okay. Moving on. Our next example, our next candidate here is water. So how many electron groups do we have with water?
3.
We have 4, which it's like, what, right? The reason for that is how many electrons does our oxygen come to the table with?
6.
6, right? And each of the hydrogens, since we know there's 2 of those, they each bring 1, right? So how many electrons do we got?
8.
We have 8, right? So we have 2 that are bonding with each of the hydrogens and oxygens here, so that takes care of 4 of them, and we still have 4 left, right? So we got to put them somewhere, and the way we do that is we have these 2 lone pairs on oxygen. Okay, so we draw the Lewis structure out like that, and again, because we essentially have 4 electron groups now around our central oxygen, they're going to want to take up their real estate too, and so we end up with the hydrogens pushed into this shape as if it was a tetrahedral electron group, but because these guys don't actually count for anything, okay, we end up with just this bent shape, right? Because there's only 3 points in terms of 3 nuclei here, and they always, 3 points always define a plane. So even though if we actually had something where these electron groups are these lone pairs, it would look like a tetrahedral electron pyramidal shape here, kind of, right? Because they're not really there, we end up with just these 3 points here in this bent shape. Are we following? This is a lot of three-dimensional thinking, so.
Yes.
Okay. And again, if you wrote it out in this wedge dash notation, you'd imagine the other 2 things sticking out here, and you would not include them because they're not really there. They're just lone pairs of electrons, so they don't take up any real space, but their electronegativity takes up space, right? So it pushes the hydrogens into this configuration. So one would be facing towards us, one would be backing out away from us, and that's how it would look. All right. How's everybody feeling about that?
Okay.
Good. Sorry I'm asking this a lot because I feel like it's hard to show you guys this stuff when it's just a one-dimensional slide. But all right, so here this table is. If you don't have it already in your book or somewhere, grab a quick screenshot because this is something you're going to want to reference for sure. We have the number of electron groups, and the way we figure that out, again, is by drawing out that Lewis dot structure to make sure we can see how many lone pairs there are and how many bonds there are. So we have that labeled here. Then we have the electron group geometry. So you can figure out what that's going to be looking at that structure. Is it going to be linear, trigonal, planar? Is it going to be a tetrahedral shape, etc., right? So if it has 2 electron groups, it's going to be linear, right? Because they're going to be as far away from each other as they can, and that'll form a line. And there'll be 0 lone pairs in some of them. So if there's just 2 electron groups and there's 2 bonded atoms, there'll be no lone pairs. The bond angle will be 180. It will be a linear shape, and an example of that was the carbon dioxide. If we have 3 electron groups, okay, our electron group geometry could be trigonal planar. Remember, 3 points always makes a plane, right, or defines a plane. So if we have 3 electron groups and there are 3 bonded atoms, we're going to have a trigonal planar, no lone pairs. And the bond angle is going to be 120. And the molecular shape is going to be a trigonal planar. And our example here was the dihydrogen carboxide. Okay, or carbonate, sorry. Phew, what am I saying? This is bicarbonate. Okay, and then if we go to 3 here, our third row down, we have 3 electron groups. It's going to be trigonal planar. If there's 2 bonded atoms, and we add a lone pair into the equation, okay, now it's going to behave a little differently, right? We're going to have a bond angle of 120, and it's going to look like a bent molecule, right? And our example here was the sulfur dioxide. Okay, so if you have 3 electron groups, 2 bonded pairs, which means we have one of those electron groups is going to be a lone pair, okay, and it's going to act just in terms of taking up real estate around the central atom. It's going to take up that much shape, but because it's not really there, instead of it being a trigonal planar looking molecule, it's just going to look like a bent molecule because there's nothing in that third space. It's just the lone electron pair. Okay, our next one here, we have 4 electron groups. So what's our shape?
Tetrahedral.
Tetrahedral. And if they're all bonded atoms, and there's no electron or no lone pairs, they're all going to be 109 degrees away from each other, so they're going to have to start taking up 3-dimensional spaces, not just planar. And the molecular shape, because again, there's 4 actual nuclei sticking out from the central carbon, it'll be a tetrahedral shape. And a beautiful example of that is what?
Methane.
Methane, yes, thank you. All right, so the next one here, if we have 4 electron groups, but one of them is a lone electron pair, this kind of changes things. The bond angle is still going to be 109, okay, but we only have 3 bonded atoms. So now we have the trigonal pyramidal shape instead, because there's nothing to stick up and create that tetrahedral shape. We have to just imagine those electrons there pushing these other atoms down into this configuration because they need their space, even though you can't see them. And our last example here was 4 electron groups. 2 of them are lone pairs. So what do we end up with in terms of the shape?
Bent.
Bent, right. So it's going to be 3 atoms, so it's going to define a plane. It's not going to be a 3-dimensional shape now. It's just going to be a bent shape like that. Okay? And water is a good example of that. All right. Okay, so I think we have an example to work through here, and then we will call it good for tonight. What I will need you guys to do is text me an address where I can drop off the model kits for you guys. I'm going to try to do that tomorrow. So wherever you'll be tomorrow, sometime midday-ish.
I'll be at work at the hospital.
Okay, I can drop them off there. That's fine. If any, please text me. If I don't get a text from you, I'll probably bother you. If you're here in town, I will try to make sure you get one. If you're not in town, we will have a separate conversation about what potentially you have available to you. I don't want you to have to go out and spend a bunch of money or anything to help you make some 3-dimensional models. And I will send you some ideas and some pictures of how to do it and all that. Okay? So,
if you're
yeah, go
going
ahead.
to the hospital, bring 2.
Okay.
Yes,
how many of you will
please.
be at the how many of you will be at the hospital? So just get a show of hands here.
I'll be
Renee, Aiden,
give it to me,
Josita.
and I'll give it to Aiden and Miss Jazita if they ever.
Okay, I'll bring you 3 at the hospital. Alan, will you? Oh, you guys are going to be at the camp tomorrow, right? Alan, Nicole, and Eve.
Yeah.
Okay, so I will bring
Um.
3 kits over there for you guys.
Okay. We're
Okay.
gonna go to Hot 366. Jerica's
Hut 366.
classroom. Yeah.
Okay, yeah, I
The
can find you there.
Inupiaq. Yeah.
Okay, perfect. I'll bring you
So
guys 3 kits there then. Who else is not going to be in town but could use a kit?
But I'll be back on excuse me, teacher one. I'll be back on Anchorage next week, but I have my lab kit already.
Okay. Do you have a three-dimensional molecular thing in your kit? Okay, so
The
I'll
bowl.
get you one too then.
Okay.
Yeah. I think we have enough kits for everybody that I can get them to. I'm not going to mail them because it'll get to you kind of late, but we'll figure something out for those of you who are at a distance. Okay.
Okay, thank you.
Yeah, no problem. All right. Okay, so we're going to walk through this example here. So we have dihydrogen sulfide here. Here's our chemical formula. That's what we're given. We need to figure out what the shape is, and we're going to be using our Lewis structures, our electron groups, and our bonded atoms to figure this all out. So our symbol for hydrogen is H, and S for sulfur. We have 2 electrons and 2 atoms here, and we have 1 for sulfur. We have 1 valence electron for each of those. We have 6 for sulfur. So our total number of electrons is going to be 8. And in order to arrange that out here, we're going to put we want to have 8 around the sulfur. So we're going to give it 2 bonds with the 2 hydrogens, and we still have 4 left over. So we're going to put them here as 2 lone pairs on either side of the sulfur like this. Okay. Usually the symmetrical choice is the right one, right? If you were to put the hydrogen down here, for example, and the lone pairs up here, it would be incorrect in the sense that the hydrogens want to get as far away from each other and the lone pairs kind of want to be on opposite sides too. So you usually try to find a symmetrical way to do it if you can, okay? As a general rule of thumb. All right, so arrange the electron groups around the central atom, minimize repulsion, and in order to do that, in 3 dimensions, it's going to look more like this. Okay, now I just said what I said in terms of the way we draw the Lewis dot, you do it that way. But then as you get into this, you're going to want to minimize the repulsion. So now you have the 4 groups around this. So this is actually 3-dimensional. Okay. Oops, go back here for a second. All right, so using the bonded atoms, the central atom here, the shape will be what? We have 2 bonded atoms. We have 2 lone pairs.
Bent.
It'll be bent, right? Because this would, I mean, if these were atoms, right, where these lone pairs are, it would be the tetrahedral shape, right? But because we only actually have 3 nuclei in this setup, it's going to be all in one plane. And because they're being pushed out away by these other electron groups, they're going to be bent like this. Okay? How does that sit with everybody?
It's sitting.
Good, good. All right. So, using our VESPER formula here, state the number of electrons and lone groups, and then determine the shape of each of these examples. So for A, what are we dealing with? Let me get my, sorry. I keep letting everybody see the answers because I keep forgetting to hit annotate before I bump my mouse. All right, so A, we have phosphorus and
trifluoride.
Trifluoride, very good. Okay, so what will be the central atom?
Phosphorus.
Phosphorus.
Phosphorus. Lexi, do you want to draw this for us? We'll do the Lewis dot first so we can kind of see what we're doing. And then we'll be able to deduce the other shapes. Is Lexi still there?
I'm here.
Okay. Okay, go ahead. If you can draw our central atom.
Yeah, I'm trying to. Oh, I'm stuck on erase from the last time.
No problem.
Sorry.
I can't tell you how many times I've done that. Okay.
Okay, there we go.
So phosphorus will be our central atom, and it brings how many electrons into the equation?
5.
5.
Fluoride each has how many?
7.
7. Okay. So we have how many electrons altogether?
7 times 3, 21 plus 5, 26.
So we got 26 electrons we got to distribute around this setup. And we know the fluorides are going to be kind of symmetrically positioned around it. Very good. Good. Okay. So go ahead and give some bonds in there between the, and you can use the lines if you want, between the phosphorus and the fluorides.
I put them where I put those dots.
Perfect. Okay, so how many electrons have we used up when we just set up 8 around the phosphorus here with a single bond to each fluoride? We've used up 8, right, for that? So how many do we have left to distribute to the fluorides?
Sorry.
We should have 18 left, right? Am I saying that right? Yes.
Oh,
So
yeah.
each of them should be able to get 6 around them, right? And that's going to be a nice, beautiful little setup there. Everybody's got 8 in their valence. Very good. Okay, so we have 3 bonded atoms and we have 1 lone pair group. So what shape is that going to make this molecule?
The triagonal planar.
Is it going to be planar?
No.
No.
Pyramid, right?
Pyramidal. Yeah.
Yeah.
Yeah. And it's going to be trigonal because it has 3 bonded groups. And it will be pyramidal because this little guy here, this lone pair, is going to push those other guys down out of its way a little bit. And if it was a bonded pair, it would create the tetrahedral shape, but it's not really there, so it's just going to be trigonal pyramidal. Very good. Excellent. Okay, moving on to the next one here. Who would like to try writing it out? I'll clear what I wrote there too. Got our next one. Ooh, we're getting really close to the end here. Would you guys like to just take a quick screenshot and work on these last 2 on your own? And we will complete this when we come back on Tuesday. So take a screenshot of this learning check. And I mean, you should have the answers in your slides and all of that, but try to work it out. Just make yourself think the steps through. Maybe not tonight, but definitely give it a try, okay? And then, like I said, I will bring those kits to everybody who's in Barrow. For those of you who are not in Barrow, I will send you, I don't have it quite, like I have the idea of it yet, but I don't have it quite figured out. So I will send you like a little informational sheet with several ideas for different things you could use, with some examples so that it doesn't get too confusing, so that you can experience trying to make a 3-dimensional molecule as well. And then I will give you a worksheet that will give, each one of the molecular formulas that we're going to be doing, and then you're going to be writing the Lewis dot structure. You're going to be naming the type of bonds that they are going to be creating in terms of are they covalent or ionic, etc. You're going to be making the 3D models and making sure that you have the name of that shape. Okay, so I won't give you too many of them, maybe 5 or 6 at the very most. And then next Tuesday, we'll kind of share with each other what we've come up with, okay? We will probably do this in lieu of a test on Pearson because, like I said, trying to do these 3-dimensional things on the Pearson is a nightmare. So I would rather that you guys actually had more of a hands-on experience for this. Is that okay with everybody?
Yes.
Okay.
So what time are you gonna be delivering those lab kits? Just a heads up for tomorrow.
What would be the best time for you?
Because everybody's at lunch at 12:30, 12:31.
Okay, so it'd be better earlier in the morning or?
11 o'clock would be okay.
Okay, I'll try to drop it off around 11. And then for those of you who are already out at the college, I'll probably get it to you a little before that because I'll go out and pick it all up, and I'll drop it off for you guys sometime around 10:45 or something like that, and I'll get the rest of the kids out to the
Shoot a
hospital.
taxi bond because I'm very forgetful and
No problem. I think I can text you. That should be fine. Yeah.
you're dropping
Uh,
them off, so